to JEE English. Okay, hope everyone are doing good. So, how is it going on? People should be tensed. Time has come closer, right? So, if you people can hear me, if you people can see me, please type in clear. Without wasting time, we will move into the lecture. If you can see me, if you can hear me, please type in clear. How many of you feel the stress? How many of you feel the stress mounting up on you because of the date coming closer and closer and closer? And one more good thing for you is that in road series, almost every chapter has been completed in less than, you can say, less than 7 hours. Almost every chapter we have put efforts to make sure that the chapter has been completed in 2 classes. That is going to be in a week. From physics, 1 chapter has been completed. So if the chapter is big, we tried our level best to complete it in less than 7 hours. If the chapter is small, automatically it is going to be completed in 5-6 hours or less than 5 hours also, right? So it's a good way for you to revise. It's a good way for you to revise. It's a good way for you to revise. Okay, Chandra has confirmed that it's clear. Okay, Sanjay, hi Sanjay, hi Kavita, hi Sultana. Okay, hi Chandu. Okay, we'll start. We will start. There is a crash course going on for you. If you people are interested, if you can afford the money, then do check it out, right? So it's going to be a properly planned crash course with a lot of DPPs and weekend tests. If you people can afford, then do join. Okay, now let's go to the core part. What are we going to do in this class? See, first we will talk about temperature and different scales, right? And then we are going to go to the core part of the chapter, which is going to be thermal expansion. And in thermal expansion, majority of the times questions are going to be from thermal expansion of solids. We will spend considerable amount of time with thermal expansion of solids. Then we will go for liquids. Then we go for gases. But gases we are not going to deal in detail. Reason being, KTG and thermodynamics is all about that. You give heat to the gas, and how the gas is going to be behaving is what we study in KTG and thermodynamics, right? Okay, so you people know that. That's why in this chapter, that is in this class especially, we talk about expansion of solids, to some extent expansion of liquids, gases superficially we are going to do, and then we are going to jump to heat and calorimetry. So from this lecture, there is high possibility that you are going to get one question in JEE main. So this 3.5 hours of class, whatever is going to be there, will guarantee you roughly 4 marks. Will guarantee you roughly 4 marks. Okay. Okay. Now, as I said, first we are going to talk about different types of scales, in which I am going to introduce my own scale, right? Thermal expansion of solids, and then effect of thermal expansion on different things, like what will happen to the time period of the simple pendulum, time loss, time gain, what will happen to the measurements with the scale when the temperature is going to be changed, right? And then thermal expansion of bodies with cavity. Like for example, you have a body, you have cut out some portion from that body, how that body with cavity is going to be expanding when you are going to heat it. And then we are going to go for thermal expansion of liquids, then gases, then we talk about heat, and then we will talk about law of mixtures and calorimetry, all of them together. That's the agenda for today's class. Okay, fine. Let's start with the temperature. Why do we need temperature? See, temperature has been introduced to measure the degree of hotness of a body. For example, we have two bodies. This is very hot, and even this one is going to be very hot. If I am trying to touch them with my hand, as they are very hot, the moment I am going to be touching them, my heat is going to get burned. Sorry, my hand is going to get burned due to the heat, right? So I can't sense literally which one is going to be which one is having a degree of hotness more, whether A is more or B is more. All I know is that the moment I touch it, I feel a lot of heat, but I don't know exactly which one is more hot. So in order to identify which one is going to be having more hotness, degree of hotness, they have introduced a parameter to measure the degree of hotness, and they call it as temperature. So temperature is used to measure the degree of hotness. It's used to measure degree of hotness. Okay, fine. Now different people have put up their own scales. Let me just take this is one. I'm trying to draw them of same size. I'm trying to draw them of same size. Okay, fine. One is used by Mr. Celsius. Let's take the other one by Kelvin. The other one by Fahrenheit. And this one is used by me. I'm making my own scale. See, all four of us are using the same length of the scale, and we have, let's say, some mercury in it. And that mercury, using these four scales, what I am going to do is, I'll take a body whose degree of hotness has to be measured. I will put this thermometer on that body. I will put this thermometer on that body. Like all four thermometers I am going to put on the body. So all four thermometers are trying to measure degree of hotness of the same body. So the degree of hotness, whatever is there for the body, will be taken by mercury, and as a result mercury gets heated up and the mercury is going to rise. Okay, and as we are using mercury, mercury doesn't know whether Celsius is dealing with it, or whether Kelvin is dealing with it, or whether Madhan is dealing with it. So basically, as the mercury doesn't know, it should respond to the degree of hotness. If something is more hot, it should expand more. If something is less hot, it should expand less. That's all it knows. It doesn't know, it's not a living thing. It doesn't know whether Celsius is handling it, Kelvin is handling it, Fahrenheit is handling it, or Madhan is handling it. So the amount of expansion in all the three cases will be what? Same. Just keep that in mind. Now let me draw a line. So the amount of expansion will be what? Same. So the length will be what? Same. Okay. Now what I'll do is, let us take this length to be small l and this length to be capital L. Now Celsius has decided to take the lower fixed point as 0 degrees and upper fixed point as 100 degrees. It's up to him. He can take whatever he wants. He has taken the lower fixed point to be 0 degrees and the upper fixed point he has taken it to be 100 degrees. And this temperature, you write it as Tc, where the temperature in the Celsius scale. Now, Mr. Kelvin has taken 273 as the lower fixed point and has taken 373 as the upper fixed point. So this reading you take it to be TK, and Fahrenheit has taken the lower fixed point as 32 and the upper fixed point he took it as 212. Now it's up to us. It is my scale. I can choose whatever I want. I want to choose the lower fixed point as 0 and I want to choose the upper fixed point as 200. That means this entire L length has been divided into 200 parts. Here, the entire capital L length has been divided into 180 parts. Here, divided into 100 divisions or 100 parts. And Celsius also has divided it into 100 divisions, 100 parts. And the temperature here, you write it as TF. The temperature of my scale, you write it as TM. Write it as TM, my own scale, and these are the famous scales. But as I said, mercury doesn't know who is handling with it, so the mercury will expand by the same amount when you are measuring the temperature of the same body. So temperature of the same body is measured with 4 different scales. Then how am I going to get relation between TC, TK, TF, TM? With the help of this small l and capital L, because the length of the scales is capital L and the expansion is up to small l. Now, you only tell me when I am going to talk about just the Celsius. Capital L has how many parts? Capital L has 100 minus 0 parts. And the small l will have how many parts? Obviously TC minus 0. Now, if I am going to talk about Mr. Kelvin has divided the entire capital L into how many? 373 minus 273, these many parts. And out of which small l will have how many parts? TK minus 273. Now, if I am going to talk about Mr. Fahrenheit, in capital L, how many parts are there? 212 minus 32. And small l, how many? TF minus 32. And if you talk about me, Madhan, capital L has been divided into how many parts? Has been divided into 200 minus 0, then the small l is going to be Tm minus 0. Now one thing, in all of us, small l by capital L is constant because all of us has taken same length of the scale and mercury has gone up by the same amount. So small l by capital L is constant for all 4 of us, right? Now, if you are going to look at, I can write it as Tc minus 0 by 100 minus 0 is going to be equal to what? Tk minus 273 divided by 373 minus 273 is going to be equal to Tf minus 32 divided by 212 minus 32 is equal to Tm minus 0 divided by 200 minus 0. Sir, why did you give this, sir? We already know it in our lower standards. We already know in our lower standards about this conversion. We have marked it up. Then why did you give it? Man, they can create their own scale in the examination. They won't talk about Celsius scale. They won't talk about Kelvin scale. They won't talk about Fahrenheit scale. They are going to make their own scale. Then how you are going to proceed? So you should have the proper conceptual understanding of how the formulas have come. That's what in fact I have given to you now. If you are going to look at, as I said, mercury just feels the degree of hotness of the body. From the hotness of the body, mercury absorbs some heat and it expands. So the expansion will be same in all the cases. Why? We are measuring the degree of hotness of one single body, the same body, but 4 different scales. So the size of the scales are same. Only thing is that Fahrenheit has divided the scale into 180 divisions, Kelvin divided into 100 divisions, Celsius also divided into 100 divisions, and I divided it into 200 divisions. They might ask their own scale, Modi scale. And in Modi scale, the starting point or the lower fixed point will be 10 degrees and the upper fixed point is going to be 180 degrees. Then in the Modi scale, what is the temperature they are going to ask? So no matter whatever might be the scale, now I am going to give you one general thingy. See, you can see the temperature we are measuring minus lower fixed point by upper fixed point minus lower fixed point is same for all the scales or not. So this is going to be helping you. Actually, the lower fixed point in Kelvin scale is 273.15, but for easier calculations, we always take it to be 273. Sir, please take dual nature part 2. I have done it, man. I think you are the one who is texting below the videos also. I am replying to you. I have done it, sir. I have done it. I have done it. Okay. Now, one small example. Generally, in competitive examinations, they are focusing on conversion between Fahrenheit to Celsius. They are ignoring the other ones. So, let us say if the Celsius temperature is 36 degrees, find the Fahrenheit temperature. It's a small question, do it. I have done the whole modern physics, I haven't left anything. So whoever it is, I have already done it. Please check the playlist. You see, you'll find my face on it. Okay, fine. So TC minus 0 divided by 100 minus 0 is going to be TF minus 32 divided by 212 minus 32. Now, you can clearly see from here the TF value is going to be 32 plus 180 into 100, 180 by 100 into TC. This is what you have to do. So, I think this is going to come out to be 9 by 5. So, this is going to be 9 by 5. So, 9 by 5 times 36. So, 32 plus 9 by 5 into 36 is going to be your answer. Elasticity and fluid mechanics. I don't know, man, when it is going to be done, but if it is left out, very soon we are going to be doing it. I think in ROAR series, almost the entire syllabus has been completed. Almost. Only few chapters are left. You can count some 3-4 chapters, I think. So all of them will be completed in near future. Okay, fine. Let's go for the core part of the chapter where questions are going to be asked. Thermal expansion of solids. Now, when we talk about solids are going to be of 3 categories. Like there are some solids where we are going to measure them in the length form. We are going to take, okay, we have a rod of length 10 centimeters. And then we take a disc of area 2 meters square. And then we talk about a sphere of volume 2 meter cube. So whenever it comes to solids, there are bodies where you can represent with a linear thing, then aerial, then volume. Right? Now look, first let us talk about, hi, good evening Mukesh. Okay, now first let us talk about linear expansion. So in that, one special thing has been observed. What is that? Coefficient of linear expansion, which is alpha. Coefficient of linear expansion represented with alpha. So how is the alpha defined? Change in length by original length per unit change in temperature is constant for a given material. If you change the temperature, let's say by 1 Kelvin, the change in length by original length per unit change in temperature is constant. For example, you take a steel rod. For steel rod, if you are changing the temperature, the fractional change in length per unit change in temperature is always constant. Steel rod might be 100 centimeters long, or it might be 200 centimeters long, or it might be 300 centimeters long, irrespective of the dimensions of the steel rod. Fractional change per unit change in temperature is coming out to be constant. Alpha is a constant, but keep one thing in mind, that alpha is going to be very small. It is going to be in the range of 10 to the power minus 5. That's why in reality, for our eyes, we can't see the difference in the lengths of the rod. When you heat it by some 30 degrees, 40 degrees, 50 degrees also, you feel that nothing has happened to the rod. Why? The coefficient of linear expansion is very, 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 very small. As a result, you can't see the physical changes that have happened to the body, but you can feel them. During winters, the doors are going to get tight to the frames. And railway tracks, if you are going to look at railway tracks, they are going to leave some gap. If they are not going to be leaving the gap, both of them will try to expand. And if they are trying to expand, if the gap is not there, then they are going to be pressing against each other and derailment might happen. It is something which you can't ignore. But can you see the visible changes? No, the visible changes are very small. Reason being the alpha is very small, but it's a very dangerous thing to ignore. Okay, fine. Change in length now can be written as what? L alpha delta T. Change in length can be written as L alpha delta T. Now look, L is what? Initial length. So to be precise, right? So final length, I will put it as L final minus the initial length which I have taken as L is going to be equal to what? L alpha delta T. So the final length of the body is going to be L plus L alpha delta T. So the final length is going to be L into 1 plus alpha delta T. So this will be the final length. But as I said, this final length will be very close to the original length, the initial length. And what is delta T? Delta T is the temperature difference you have created for the body. Temperature difference you have created for the body. If you want to understand it in even better way, look. If you have some L length of it, when the temperature of this one is going to be T, the length of this one is going to be L final when the temperature of the body is going to become T plus delta T. T plus delta T. Mosquito. Okay. Now, let us do a small question on it. 2019 JEE mains. Man, majority of my session questions I'll try to pick from 2019, 2020, and if possible some 2021 also, because these are the years where the JEE mains paper has come difficult. 2020 is a nightmare. It is close to advanced level. 2021 slightly close to advanced level. 2022 bit better. 2023, 2024 is nonsense. You won't even call it as JEE mains. It's like some CET examinations of the state boards. I feel that they are going to increase the level. For sure, they are going to increase the level. If not on 2020 level, at least they will touch 2021 or 2022 level. Okay, super clear. Thanks, Sanjay. Then get me the answer for this. Two rods A and B of identical dimensions are at temperature 30 degrees Celsius. Both of them are at same temperature, which is 30. If A is heated up to 180 degrees and B up to 3 degrees Celsius, then the new lengths are also same, right? If the ratio of the coefficient of linear expansion of A and B is 4:3, then the value of T is, initially both of them are at 30, and now they are asking you to calculate Both of them are at 30. Both of them have same dimensions also. Identical dimensions is what they have mentioned. Okay, now look. Now look. Both the rods. Both the rods. Both the rods. They have same length initially. They have same length initially. So this fellow is A and this fellow is B. And both of them are at 30 degrees Celsius. 30 degrees Celsius. Now they have heated them. They have heated. But we know to what temperature the other, like the first one is heated, that is A. A is heated till where? A is heated up to 180 degrees. But this one, we don't know, it is heated to some T degrees Celsius. Now, both of them have same final length, man. Final length of A is equal to the final length of B. Right? So I can write L into 1 plus alpha delta T. What is the change in temperature? Can I claim it to be 180 minus 30, which is 150? So alpha A into 150 is going to be L into 1 plus alpha B into the temperature of this one we don't know. So it is going to be T minus 30. Right? So L and L are going to get cancelled out. So from here, if you talk about alpha A by alpha B is 4:3. So I can write alpha A by alpha B into 150 is going to be equal to T minus 30. And for your kind information, alpha A by alpha B can be written as what? 4:3. So 4 by 3 into 150 is going to be T minus 30. So you are going to have this to be 50 into 4, which is going to be 200 plus 30. So the T is going to be 230 degrees. So which option? Option 2. Option 2. Now I would like to give my own question over here. I hope everyone are clear with this. If you are clear with this, make sure to press the like button. If you are clear with this, make sure to press the like button. Okay, my own question. Look, we have two rods. Having same initial length and coefficient of linear expansions alpha 1 and alpha 2, and both of them are initially at same temperature. Okay, just a second. Two rods, I won't say same initial length, same initial temperature. And coefficient of linear expansion alpha 1 and alpha 2. Right? What should be the relation between the initial lengths? What should be the relation between the initial lengths such that difference in the lengths at any temperature is constant, such that difference in lengths at any temperature is constant, indicating the difference in the length is temperature independent. See, if they are going to say that the difference in length is constant, that means no matter whatever might be the temperature you are making those rods reach, the difference in the temperature is not depending on that, difference in their length is not depending on that temperature. I hope the question is clear. Okay. Now look, what I mean is we have a rod, not a rod, we have in fact two rods. Let us take one rod to be this, other rod to be this. We have length of this one to be L1, we have length of this one to be L2, and both of them, these are the initial lengths. This one, let us take that initial temperature to be T0. What is the difference in the length? L2 minus L1, initial difference. What is the initial difference in the length? Initial difference in the length is going to be automatically L2 minus L1. Now, as you increase the temperature of them, automatically length is going to get changed. What will be the length of this one? The final length of this one is going to be initial length into 1 plus alpha 1 delta t. What will be the final length of this one? The final length of this one is going to be initial length into 1 plus alpha 2 into delta t. And what did they say? This difference, whatever will be there, is remaining constant. It is not depending on the temperature of the rods. Okay, fine. So what is the difference in the length then? It is going to be L2 into 1 plus alpha 2 into delta t minus L1 into 1 plus alpha 1 into delta t. Right? Now this is where you have to use your common sense. Look here, L2 alpha 2 delta t, here minus L1 alpha 1 delta t is there. So the delta L is going to be L2 minus L1 plus, from here L2, from here minus L1. So L2 minus L1. Next, we have L2 alpha 2 delta t, we have minus L1 alpha 1 delta t, which is going to come out to be L2 alpha 2 minus L1 alpha 1 into delta t. Now it is very clear that the difference in the length should be constant. That means it should not depend on the temperature. Temperature term should not be there. For delta L to be constant, when I say for the difference in length to be constant, indirectly I am saying it should be independent. Of temperature. That means for difference in length, delta t should not be present. For delta t to be missing, we have to multiply it with what? 0. If it is multiplied with 0 into delta t, then the delta t term won't be there. So for delta t to be missing, this part has to be 0. L2 alpha 2 minus L1 alpha 1 is going to be what? If it is 0, then what will be L1 by L2? It is going to be alpha 2 by alpha 1. So if the initial lengths are in this ratio, then what will happen? The change in length will simply be L2 minus L1, where L2 is the initial length of the second rod and L1 is the initial length of the first rod. That's it. You can't see any temperature to be present in this equation. That means no matter whatever might be the temperature of the rods, difference in lengths will always be constant. So this is one good question which you people should keep in mind. This is a good question which you people should keep in mind. So it's a famous question also. Once again, I am repeating, they are going to talk about two rods of some different initial lengths. Both of them are at same temperature. What should be the ratio of their lengths, or what should be the relation between their initial lengths, such that difference in lengths of these two rods at any temperature will be constant. That means it should be temperature independent. Okay. Next, I already said to you, when we talk about solids, are we going to have only rods? No, there will be bodies which are going to be spread over area. There will be bodies which are going to be spread over volume. So when I talk about solids, I have to be careful. Sanjay, super. Okay. Areal expansion. Areal expansion. Areal expansion, sometimes also referred to as superficial expansion. Both of them are same. Now here, coefficient of areal expansion or superficial expansion is going to be represented with a symbol beta. So how is the beta defined? Beta is going to be fractional change in area. That means delta A by A per unit change in temperature is constant for any solid. Okay, fine. The same old story goes now. So A is going to be, or delta A is going to be A beta into delta T. So delta A is what? Change in area. That means final area minus the initial area is going to be A beta delta T. So the final area is going to be A into 1 plus beta delta T. This is mathematical. Let us look at exactly what happens. Man, we have a body. Let us take this. It has a length L and it has breadth B at some temperature T. Now, if you are going to be increasing, okay, for you to have better understanding, this is the one we are talking about, which has spread over area. Mass is spread over area. Now, if you are going to be increasing the temperature of it, what will happen, man? If you are going to be increasing the temperature of it, for sure, its area will change. Okay. Now, if you talk about L is linear length, right? L is length, B is breadth. That is also going to be what? A linear measurement. And we know how the linear measurements are going to expand. How the linear measurements are going to change, I know. If the temperature of this is going to be made to go to T plus delta T, then the change in temperature is delta T. Then the final length of the one of the side will be L into 1 plus alpha delta T. And what will be the final breadth? B into 1 plus alpha delta T. Now you tell me, what is the initial area? Initial area is L into B. What is the final area now? The final area we are talking about is L into 1 plus alpha delta T into B into 1 plus alpha delta T. Because this is the final length, this is the final breadth. Okay, super good. Next, let's take it to the next page. So the final area is going to be L into B into 1 plus alpha delta T whole square or not? Whole square or not? Yes. Charumati, good evening. Good evening, sir. Thank you for your hard work in both English and Telugu channels. Sanju, thank you. Okay, now look, I already mentioned to you that alpha is going to be very small. Alpha is very small. Okay, in that case, let me think of binomial approximation. 1 plus x to the power n can be roughly written as 1 plus nx. When we can write that? Never ever forget, we can write this one only when the x is going to be very, very small. Only when x is going to be very, very small when compared with 1. Sir, how small? So, x being 5% of 1, that means 0.05. X value up to 0.05 will be taken as very small, and you can use that approximation. Now, every one of you know that alpha is in the range of 10 to the power minus 5. Alpha is very small. So that means alpha delta t is also going to be small. So in that case, alpha delta t can be compared with what? X. Alpha delta t can be compared with what? X. And do the expansion. Then do the expansion, the final area. The final area is going to be L into B into 1 plus 2 times X, which will turn out to be what? 2 alpha delta T. Man, this final area can be written as what? The initial area into 1 plus beta delta T is going to be L into B into 1 plus 2 alpha delta T. Now you only tell me what is the initial area. Let us go back in slide. What is the initial area? The initial area is L into B, right? So the initial area is L into B. So can I kick these things off, like cancel them off? Yes. And then after comparison, what is the relation? The coefficient of aerial expansion is 2 times the coefficient of linear expansion. For your kind information, right in front of your eyes, you can see that. Right in front of your eyes, you can see that area of a body is changing. Right in front of your eyes, area of a body will be changing, but they won't give beta, they'll give coefficient of linear expansion. Why? They're expecting you to know the physics behind it. If alpha is given, 2 times the alpha is beta. Once you get beta, then you can talk about the changes in area. That's what they were expecting. Keep that in mind. So don't think that always they have to give beta if there is change in area. Sometimes they are going to give alpha. Okay, now we also have bodies. We also have bodies where volume is going to change. Solids, na? Length, area, some of the bodies are going to be occupying volume. Okay, now here I'll talk about volume expansion. When I am talking about volume expansion, here also I'll just talk about coefficient of volume expansion. Coefficient of volume, coefficient of volume expansion, represented with the symbol gamma. How is this defined? So the gamma is going to be fractional change in volume per unit change in temperature. Even this is a constant. Okay, from here, the change in volume can be written as initial volume into gamma delta T, and then the final volume can be written as initial volume into 1 plus gamma delta T. Is there a way we can relate alpha, beta and gamma? So for that, what I will do is, I'll just take a cube or cuboid. Rather than saying cube, I'll take a cuboid. what I'll do is, I'll take this to be L, I'll take this to be B, I'll take this to be H. Now, if I am going to be increasing the temperature, if I am going to be increasing the temperature, for example, this body, oh shit, this body is at some temperature T, and now I increase the temperature of this one to some T plus delta T. As a result, the volume of this will change. So the linear length is no longer L, it is going to be L into 1 plus alpha delta T, B into 1 plus alpha delta T, H into 1 plus alpha delta T. Right? Now, what will be the final volume? What is the final volume? The final volume is going to be obviously final length, which is going to be L into 1 plus alpha delta T, B into 1 plus alpha delta T, and H into 1 plus alpha delta T. So now the final volume can be written as L into B into H into 1 plus alpha delta T cube. Same, we can use binomial approximation. Alpha delta T is very small. So in that case, the final volume is going to be L into B into H into 1 plus 3 alpha delta T. I am not explaining step by step. Now, final volume can be written as what? Initial volume into 1 plus gamma delta T is what we can write. Is going to be L into B into H into 1 plus 3 alpha delta T. So this and this can be cancelled out. So from here, gamma is going to be what? 3 alpha. So I can say that if I am going to talk about the ratio, alpha is to beta is to gamma, I can write it as alpha is to beta can be written as what? 2 alpha, gamma can be written as what? 3 alpha. So it is going to be 1 is to 2 is to 3. That's the ratio. Now keep in mind, right in front of your eyes, we can see that there is changes in volume, but they won't give the coefficient of volume expansion, that is gamma, they'll give alpha, because they're expecting you to know that gamma is 3 times alpha. Kanupasami, we are doing 11th, thermal expansion. Ashwin, so how long this session is going to go? The session is going to be, what is the time now? It's 6:20, right? So roughly 2 hours, 2.5 hours more. Okay, fine. We got the ratios. Now, this is one important thing which you people should know. Bimetallic strip. Bimetallic strip. So what is that bimetallic strip? Man, in the name itself, you can clearly see you have 2 of them, right? We will have 2 strips put together. We will have 2 strips put together. 2 metallic things are going to be put together. This is one, and one more. I'll use a different color. This is the other one. Both of them are welded together, but the problem is this one has coefficient of linear expansion alpha 1, and this one has coefficient of linear expansion alpha 2. Let's take alpha 1 to be more than alpha 2. So if I am going to do any changes in temperature to this bimetallic strip, who should expand more? Whichever is going to have more linear expansion is going to be expanding more, right? So the bimetallic strip bends. to accommodate the extra length. Whichever is going to be outer is the one which is going to be having more length. Whichever is going to be the inner one, that's the one which is going to be having lesser length. I'll talk about it, but keep in mind, if you talk about the thickness of this, it is going to be T, and the thickness of the green one is also taken to be T. Now, if temperature of this bimetallic strip, if temperature is increased by delta T, initial length, let us take the initial length of both the rods to be some capital L. So what will happen if you increase the temperature? The strip is going to bend. And how it is going to look like? How it is going to look like? Man, it is going to be bending like this. Why it is going to be bending like this? Because the orange one has more alpha, it should expand more. If it has to expand more, it should have more length. If it has to have more length, then it should be on the outer side of that bending. If it is onto the inner side, its radius will be less. As a result, its length will be less. So, I can claim that, look here, right? Now look everyone, this interface whatever is there, I am taking the mean radius of the strip with the interface. So this is what I am claiming as the capital R. They are going to ask the capital R value. They are going to ask the capital R value, where capital R is the radius of curvature of that interface. But for the green one has less radius, right? So use your common sense once. If you use your common sense, the green one's mean radius is going to be passing through the center of the green one, right? So as the thickness of it is T, so if you are talking about passing through the middle, then the distance between red and the purple one is going to be how much? T by 2. Then automatically what will be this length? This length is going to be capital R minus T by 2. Now if I am going to talk about that orange one, the orange one will have its mean radius passing through here. Obviously that also you have to talk about. What will be the mean radius of that orange one? It is capital R plus T by 2. That's why, man, as this one has more length, even though both of them are subtending same angle, green and the orange, both of them are subtending same angle, but length of the orange one will be more because its mean radius is more. So they are going to ask questions. How they are going to ask questions? How the shape will bend. The straight bimetallic strip, will it bend down or will it bend up? It all depends on which is having more alpha. Whichever is going to have more alpha should have bigger radius. If alpha 2 is more than alpha 1, then the bending should have been up, such that green will be on the outer side of the circle, such that the mean radius of the green will be greater. Very tricky and very interesting. Very tricky, very interesting. Damn good. Now our aim is to calculate that R's are. Right? So what is the length, final length of the orange one? What is the final length of the orange one? Final length of the orange one. Final length of the orange one. The final length of the orange one can be written as what? Length of the arc, R plus T by 2 multiplied with theta. And what will be the final length? The initial length. What is the initial length? L into 1 plus alpha 1 into delta T is going to be R plus T by 2 times theta. This is our first one. And then we have the green one, and the green one is having how much final length? It is the average radius of the green one is R minus T by 2 into theta. What is L final? It is going to be L into 1 plus alpha 2 into delta t is going to be r minus t by 2 times theta. So this is our equation 1. This is our equation 2. Is theta needed for us? What was asked from us? We have to find the radius of curvature of the bimetallic strip when it bends. That means we need capital R. We don't need theta. How can I get rid of theta? If I divide equation 1 with 2, theta gets eliminated. Right or wrong? If I divide equation 1 with 2, theta gets eliminated. Now, what will happen? Equation 1 divided by equation 2 will give you, L also gets cancelled out, man. LHS side, L also will get cancelled out. So 1 plus alpha 1 delta t by 1 plus alpha 2 into delta t is r plus t by 2, right, by r minus t by 2. Now our aim is to calculate what? R value. Our aim is to calculate R value. Okay. Then we can, what we can do? Cross multiply. You will get R minus T by 2 plus R alpha 1 delta T. I am directly doing the calculation. Minus T by 2 into alpha 1 delta T is going to be here R plus T by 2, because this when you multiply with 1 it will be R plus T by 2. Then R should be multiplied with R alpha 2 into delta T, and then T by 2 into alpha 2 into delta T. What all can be kicked out? See, this R and this R can be cancelled out. And whatever we need, we will keep them onto the, like whatever we need to calculate, we'll keep it onto the LHS side. Rest we will take it to the RHS side. Then you can see we have minus T by 2, and on that side we have plus T by 2. So minus T by 2, when it goes on to that side, it is going to be plus T by 2 plus T by 2, which will be T. And this R I have to take it this side, this I have to take it this side. So then R into alpha 1 minus alpha 2 into delta T is T plus T plus T into alpha 1 plus alpha 2 by 2 into delta T. I can write like this. Now, I have a small question, man. When compared with the thickness, this term will be very, very small. This term is very, very small when compared with the T. Why? Alpha 1 plus alpha 2 by 2, man, alpha is in the range of 10 to the power minus 5. So I can ignore this term when compared with this. Then what will come out to be the radius of curvature? It will come out to be small t, which is thickness of each strip, each element in the strip, by alpha 1 minus alpha 2 into delta t. So this result, whatever is there, is very useful for you. You can write it down somewhere when you are revising the formulas. Along with the formula, you should see this result. So you write this as one formula. You write this as one formula, ready-made formula kind of thing. If this question comes, 99% of the people won't be able to do it in the examination. You being my students have got this. Bhargavan, sir, I have a doubt in dual nature chapter, sir. Where can I approach you, sir? Please comment below the video. Please comment below the video. All the comments I read. I read all the comments. Okay, fine, nice, good, done. Now, what effects we are going to have on the simple pendulum? This is one more nightmare for majority of the students. Time loss, time gain, they won't be able to understand why there is time loss, why there is time gain. Clearly, properly, I am going to explain now. Okay, man, let us talk about A simple pendulum. When I talk about a simple pendulum, let us take the length of it to be some L. What will be the time period of the simple pendulum? It is going to be 2 pi under root of L by G. And one more small thing, man, to avoid confusion, T is time period. So when we deal with simple pendulum, T is going to be time period. Temperature we will represent with theta. So when we deal with simple pendulum, T is going to be what? The time period. T is going to be time period, and theta is going to be representing the temperature, because I don't want you people to get confused. Theta represents temperature, T represents time period. Now, man, this is well and it's good, nice. If you change the temperature, if you increase the temperature, what will happen to the length? Length is going to change. If the length is going to change, will the time period change? Yes. As temperature increases, length changes. So will be the time period. Not only increases, if temperature decreases, then L value decreases, then the temperature is time period is also going to change. How much it is going to change? Man, we don't need to do any calculations here. Luckily, we can use differentiation. Why? Differentiation can be used when you have small changes. Luckily, all thermal expansions of solids are going to result in small changes. If you talk about the change in length, for your naked eye, you can't even see the changes in the length when temperature is going to be increasing. Reason being, the changes are very small. So when changes are very small, we can use when changes are very small, we can use differentiation. We can use differentiation to find those changes, because lot of students have a problem. Their teacher sometimes will do differentiation, sometimes he won't do differentiation. Then student is going to be like, man, when to use differentiation, when not to use differentiation. That's a big problem. Sometimes my teacher suddenly does differentiation. How I will get the idea? This is how you get the idea. When the things that are in front of your eyes are changing small, then definitely you can use differentiation. Bhargavan AC will be done by Shreyas sir. I think he has done EMI, so slowly he'll complete AC also. Now look. So hope everyone are conceptually clear. When to use differentiation. Now, when length changes, how much change in time period will happen? So I'll differentiate. So it is going to be 2t into dt 4 pi square by g is a constant. So differentiation of L is dl. Now what I'll do is, on both the sides, I will divide with t square. That means t square will be what? 4 pi square L by G. So now you get what? 2 times dt by t is going to be dl by L. Okay, nice. Let us take the 2 this side. So the change in time period by the original time period is going to be half. dl can be written as what? Change in length can be written as what? Initial length into alpha, change in temperature. But here temperature is represented with theta divided by L. So L and L are going to get cancelled out. So the fractional change in temperature, fractional change in time period is half alpha delta theta. A very, 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 very important result. A very important result. So, if temperature changes by delta theta, the new time period is going to be the old time period plus the change in time period. This is the new time period of oscillations. This is the new time period of oscillations. Let us talk about cases. Let us talk about cases. Man, one more thing. Whatever you are going to be replying, I'll read everything. Right? When situation comes, I'll clear your doubt. Whatever you have written it in the comment box. All of a sudden in between concept, I can't break the concept and clear your doubt, right? I'll just look through all the comments. Whatever the problems you have, you just write it down over there. I'll definitely be taking care of them if I can. Okay? Now look. Sir, I want to see what will happen if temperature increases, sir. If temperature increases, what will happen? I want to see, sir. If temperature decreases, what will happen? That also I want to see, sir. Okay, let us deal. Ayyo, shit. If temperature increases, that means theta increasing, then delta theta will be what? Positive. If something is increasing, change of it will be positive. Okay, fine. Now look. Let us go back. If delta theta is positive, dt will also be positive or not? Change in time period. Change in time period or dt. Even dt is going to be what? Positive. Indicating what? The change in time period positive means time period has increased. So I'll explain this with an example. The new time period, like old time period. The old time period which we represent with the t, let us take it to be, let's say, some 2 seconds. But the new time period, as the temperature increased, the new time period has increased, and let us say it is some 2.016 seconds. This is the new time period. Okay, now in olden days, they don't have digital clocks. Right? If there is someone who is measuring the time with a simple pendulum, how are they going to measure time, man? They'll make one person sit. Right? And they are going to order him. They are going to give orders to him that, man, every time the pendulum has completed one oscillation, count it as 2 seconds. That fellow, that poor guy who is getting paid to count the number of oscillations, he doesn't know physics. As the temperature changes, the time period of oscillations will change. He doesn't know all of it. What he knows is that, one oscillation, that is to go from here to here and to come back from there to here, that is to complete one oscillation, the time it takes is 2 seconds is what is said to him. Each oscillation will be counted as 2 seconds. He doesn't know physics. When he is measuring, temperature has increased, let's take it to be summer. Temperature has increased, so the length of the pendulum has increased. As a result, time period increased. So the real time is this. But he will count it as what? This. Are you able to understand? Are you able to understand? Man, this fellow, he doesn't know all this, time period will change and all those things. He doesn't know, poor guy. He is not educated. Or even if he's educated, he's not from the science background. Even if he's from the science background, okay, he didn't take up physics to this level. So that fellow is sitting over there. He will just count one oscillation as 2 seconds, but actually it is 2.016 seconds. So in this situation, that fellow, that poor guy, he is going to be measuring 2.01 seconds will be read as 2 seconds. So he's counting more time as less time. It's a time loss. So how much is the time loss? So we have time loss in this case. We have time loss in this case. So what's happening? For every 2.016 seconds of real time, 0.016 seconds is lost. And for your kind information, what is that 0.016? It's the dt, change in time period. And this is the original one. Right? Are you able to understand? So, for every new time period, there is how much loss? Dt amount of loss is there. So if someone is going to ask in certain time, how much is the loss? So the loss is going to be what? Dt into small t divided by t nu. This is what you have to use, right? And this is roughly equal to dt by the old t into small t. Why? The new time period and the old time period are more or less same. Slight change will be there, but more or less they are same. So while doing calculations, the new time period, whatever is there, if you put it as the old time period also, the calculations won't change much. And what is this dt by t? This is half alpha delta theta multiplied with the t value, where t is the actual time. They are going to say in 24 hours how much time is lost. So if they are going to talk about how much time is lost in 24 hours, half alpha delta theta into 24 hours. If they ask how much time is lost in 1 week, in 1 week, 1 week is going to be what? 7 days, 7 days will have 24 hours, 24 hours, each hour will have 60 minutes, each minute will have 60 seconds. So half alpha delta theta into 7 into 24 hours into 60 minutes into 60 seconds, that much will be the loss. If you want exact answer, you have to put the new time period, which is 2.016. If you want rough answer, you can put the time period as 2, right? Rough calculations. Now man, exact opposite is going to be happening if temperature decreases. If temperature increases, we have time loss. If temperature increases, we have time loss. Temperature decreases, reverse effect. Less will be counted as more. So you'll have time gain. If you have loss here, then the opposite is going to be gain. Don't think much. Exact reverse will be obviously gain. If temperature decreases, if temperature decreases, what will happen? Delta theta will be negative. Delta theta will be negative. As a result, change in time period will also be negative, because change in time period is going to be half alpha delta theta into the capital T. So for you to understand, I am just taking an example. So the normal time period to be 2 seconds, but the new time period is, let's say, 2. Its new time period is t plus dt. Let us say 2 plus some minus 0.16. It will be very small, so let us write like this. Then you are going to have 1.9 1.984 seconds. This much. So that poor fellow, whoever is made to sit to count the time with the number of oscillations of the simple pendulum, what will happen? For every oscillation, this fellow will read it as 2 seconds. Every oscillation will be read as 2 seconds. That is, now 1.984 seconds is read as 2 seconds. That means for every 1.984 there is a time gain of 0.016. So for every 1.984 seconds we have a gain of 0.016, which is nothing but what? Magnitude of the change in time period. Why did I put magnitude of change in time period? Change in time period is actually negative. Okay, fine. In certain amount of time, how much is the gain? Right? So this can be written as what? The question mark is going to be written as what? Obviously 0.016 divided by 1.984 into t. This can be approximately written as dt by t into small t. So this is also going to be magnitude of half alpha delta theta into t. So time loss or gain can be easily calculated in this way. So this is the theory which I have given. So a lot of theory has been fed to your mind. Do a question. Do it. A seconds pendulum clock has a steel wire. The clock is calibrated at 20 degrees Celsius. Man, wherever it is going to be calibrated, if you operate at that temperature, it gives proper reading. How much time does the clock lose or gain in 1 week when the temperature is increased to 30 degrees? If temperature increases, we will have time loss or time gain? Obviously loss. Because more time will be read as less time. As a result, we will have loss. Okay? Now, if you want the shortcut without using any of the common sense, simply if you want to use shortcut, if you want to get a answer which is very close, man, you know very well that dt by t is going to be what? Half alpha delta theta. Mug it up if you are in need, and this should be there in the list of the formulas where you are going to write for this chapter. This should be there. Okay, we are talking about seconds pendulum. Seconds pendulum time period is 2 seconds. Right? So what will be dt from here? See, look, half alpha value is how much, sir? 1.2 into 10 to the power minus 5. What is the change in, sir? Temperature 30 minus 20, which will be 10 into 2 seconds time period. Right? So 2 and 2. As a result, what will be the dt you are going to get? You are going to get 1.2 into 10 to the power minus 4, which is going to be how much? 0.00012 seconds. So the time period change is positive. That means the new time period, man, I am going to do proper calculation over here, and then I'll use approximate method also. Directly, I won't go for the shortcut. I'm just using common sense now. Later, I'll use the shortcut. I'll compare how much time difference is there, right? Bear with me. The new time period will be, obviously old one is 2. Now this is the change. So the new time period is 2.00012 seconds, man. Okay, now look, this much time is counted as 2 seconds because in this much time the pendulum will complete one oscillation. The person, whoever is sitting, he sees one oscillation completed, he will note it down as 2 seconds. That means 2.0012 2.0012 seconds is read as 2 seconds. Is read as 2 seconds. That means for every 2.0012 seconds there is a loss of 0.00012 seconds. Okay, super good. We found out. So now look, we have to just do the math. 2.00012 seconds. For every this much, how much is the loss we have? We have 0.0012. And we need loss in 1 week. 1 week is going to be what? 7 days, 24 hours, 60 minutes, 60 seconds. So we need the loss in this much amount of time. So how much is it? You cross multiply. I'll use the calculator over here. It's going to be 0.00012 into 7 into 24 into 60 into 60 divided by 2.00012 gives us 36.2858. So how that question mark is going to come? The question mark is going to be 0.00012 into 7 into 24 into 60 into 60 divided by 2.00012, which will turn out to be how much? 36.2858. This is the exact answer. 36.2858. These many seconds will be lost in 1 week. This is the exact answer. What is the rough answer? What is the rough answer? Rough answer, not the exact one. Rough answer, not the exact one. Man, we know that change in time period by the original time period is half alpha delta theta. In fact, whatever the change in time period is there, that's the loss we are going to have for every t. Right? Now look, if I am going to talk about the loss is going to be this dt. Go back. Where is this? Yes. How to get the loss? dt by t into small t, where small t is the total time they are talking about. dt by t into small t, and dt by t is going to be what? Half alpha delta theta into t. So I'll directly write from previous slides, I can directly write the loss to be half alpha delta theta multiplied with the time. Now you tell me, half alpha is how much? 1.2 into 10 to the power minus 5. Delta theta is how much? 10. We are talking about 1 week, 7 days, 24 hours, 60 minutes, 60 seconds. So if I am going to talk about the rough calculation, what is the answer going to come out to be? 1.2 into 7 into 24 into 60 into 60 divided by 2. We get 36.2880 seconds. So this is a rough calculation and this is exact calculation. It is 36.2858. Rough calculation 36.2880. So in the third decimal place we are getting the answer to be different. Can't we use this rather than going like this? It's up to you how you want to, but I personally prefer this. But there will be some students who are going to be like, sir, I can't think of that and all. I'm not, like, I can't concentrate in the examination. Who is going to go through all of this? I want a simple formula. So simple formula for you is loss or gain is this one. So one final formula and one simple formula which I would like to give you is that a simple formula, see whether it is going to be time loss or time gain, whatever they are talking about, whether it is time loss or time gain, simply you write it as modulus half alpha delta theta into the time whatever they asked you to find in. That's it. That's it. Okay. How much duration? Man, roughly it is going to be up to 9 o'clock. Roughly it is going to be up to 9 o'clock. This question. Do it. It's a good question. People struggled that year. People struggled that year when this question has come. A pendulum clock loses 12 seconds a day if the temperature is 40 and gains 4 seconds a day if the temperature is 20 degrees Celsius. The temperature at which the clock will show correct time, man. If you are 40, then it's a loss. That means you are operating it more than the calibrated temperature. At calibrated temperature, it gives exact reading. If you operate higher, there will be loss. If you operate lower, there will be gain. That means the calibrated temperature is between 20 and 40. Can we eliminate options? Yes. So calibrated temperature is definitely not 60, definitely not 55. So your answer has to be between 1 and 3. Your answer has to be between 1 and 3. Your answer has to be between 1 and 3. Okay. The temperature at which the clock will show correct time and the coefficient of linear expansion of the metal of the pendulum shaft are respectively. Okay. I'll directly go for the rough thing. Right? I'll go for the rough thingy. What is that? If I am going to talk about loss or gain, it is going to be half alpha delta theta into the time they are talking about. So they said loss of 12 seconds. So half alpha modulus, right? So higher temperature minus lower temperature. I should write 40 minus T into 1 day. Next, what about gain? So gain is going to be modulus half alpha delta theta into T. So the temperature here should be written. If you want this to be coming out positive, you have to put higher temperature minus lower temperature. 20 degrees is lower temperature. Okay, what is the gain? 4 is half alpha. I should put T minus 20 is this, right? This is your equation 1, this is your equation 2, and our aim is to calculate first of all the temperature. So if I am going to divide, small t gets cancelled out, alpha gets cancelled out. Okay, equation 1 divided by equation 2 is going to be what? 12 by 4 is 3. Half gets cancelled out, alpha gets cancelled out. It's 40 minus t divided by t minus 20, which will be what? 3t minus 60 is going to be 40 minus t. So you get 4t to be equal to 100. So the calibrated temperature is 25 degrees Celsius. Done. Which option? Option 1. And I started teaching from 2015. 2016, even best of the students have struggled with this question. Best of the students. To be precise, in 2016 I was teaching in Bengaluru, and I was teaching in an institute called as Diksha, right? That year the student who has gone to NIT Surathkal doing computer science over there, that fellow, he didn't get this question. He didn't get this question. Okay, fine. Now look, man, this effect of temperature didn't even leave the measurements made with the scale. Let us see how that is going to get affected. Let us see how that is going to get affected. Let us take oh, what happened, man? Are you? Let us take this much length to be, some 10 centimeters. This is the actual 10 centimeters. Let us take that actual 10 centimeters. Now what I'll do is, I'll take a metal scale, and what I do is, I'll take a metal scale, and what I will do is, I'll take a metal scale of this much length, and this, let's say, is at 30 degrees Celsius. So at 30 degrees Celsius, this metal scale has this much length. That means its original length is how much? 10 centimeters. Now what I'll do? I will do markings. So this is 0th division, first, second, third, fourth, and so on. And this is my 10th division, indicating that each division on the scale is going to be 1 centimeter. Indicating each division is going to be 1 centimeter. Now, man, what happened is that I increased the temperature where the measurements are being made. Then automatically what will happen? Length of that metal thing, whatever I have taken, is going to change. For example, let us take, I am using this scale, let's say in Rajasthan, and during peak summer, there the temperature, let's say, is 45. Then what will happen? This much length will become this much length. But I have a small question. The ink on the scale, where I have made the markings, does it know all these things? It's not a living thing. It doesn't know anything, right? It is not going to be like this. Arey yaar, come on, the length of the scale is increasing. So as the length is increasing, I will put new readings on my own. Will the ink do that? No. Ink will not do any such kind of thing. So what will happen? The starting point will be your 0 only. The ink starting point will show 0 and the ending point will show 10. So if you are going to use this scale, what it reads, for example, if I am trying to measure length of this thread, length of the thread is clearly more than 10 centimeters. But when I measure this thread with this scale, what the scale sees, okay, one end of the thread is at 0, other end of the thread is at 10. So the scale says that, man, it starts at 0, ends at 10. That means it is going to be exactly 10 centimeters. Scale reads it as 10 centimeters. So if you are operating the scale, at higher temperatures than the calibrated temperature, more length will be read as less length. Okay, now I am taking the very same scale to, let's say, Himalayas. At Himalayas, every one of us know that the temperature is less. So let me take that the temperature, let us take it to be some 0 degrees Celsius. Then what will happen as the length has changed, the 0th division on the scale will be here and the 10th division will be here, and now I will take a thread whose length is this much. So if I am going to talk about length of the thread is less than 10 centimeters clearly. Length of the thread is less than 10 centimeters. But what the scale says, man, one end of the thread is at 0, other end of the thread is at 10. So I can clearly see that the reading is 10 divisions and each division is 1 centimeter. So 10 divisions, 10 centimeters. So what the scale reads? Scale reads it as 10 centimeters. So what is happening? If you are going to be operating the scale at a temperature which is going to be less than the calibrated temperature, less length will be read as more length. If you are operating the scale at a temperature more than the calibrated temperature, more length will be read as less length. This much conceptual clarity you people should have. Whenever you get any doubt, you draw a reference diagram like this. Okay. Do this question then. A steel ruler exactly 20 centimeters long is graduated to correct measurements at 20 degrees. That means if you operate that steel ruler at 20 degrees, it gives proper reading. Will it give readings that are too long or too short at lower temperatures? Answer this. Come on, everyone. Please type in the chat box. Come on. Please type in the chat box. Oh. For you to 1 second. I think now it's a bit bigger. I think you people can read it. Please type in the comment box, the chat box. Will it give readings that are too long or too short? If you are operating it at lower temperatures, less length will be read as more length. Come on. It's a very clear thing, right? If you are going to be operating at lower temperatures, what will happen? If you look at the length of the scale, right, the true length of it, look, these dotted lines, the length between these dotted lines is 20 centimeters, and that in fact is the length of this steel one at 20 degrees Celsius. Now if you are operating at smaller temperature, obviously the length of the rod gets shortened, right? So the actual length of this one will be less than 20 centimeters. But we have done calibrations this is the 0th division, and let's take this is the 20th division. Now obviously those calibrations whatever we have made, those markings whatever we have made, they won't change. So as a result, what will happen? A length which is less than 20 centimeters will be read as 20 centimeters. Length less than 20 centimeters will be read as 20 centimeters. So less length is measured as more length. Sanjay, not same. I hope now you understood. Chat, in the chat box you type in. If you have understood, type that understood sir, clear sir. Otherwise, I'll explain for you again if needed. What will be the actual length of the ruler be when it is used in desert at a temperature of 40? If you are using it in desert at 40 degrees, what will happen now? This ruler will have a length more than 20, but the readings, whatever the markings I made, that won't change. They will remain as it is. So if you look at this length is definitely more than 20 centimeters. So more than 20 centimeters will be read as 20 centimeters. Now I want to see how much will be read as 20 centimeters. For that I need to know the length of this rod at 40 degrees. Length of the rod, length of rod, or you can say that steel ruler, length of steel ruler at 40 degrees Celsius is going to be the final length of it, initial length 20 centimeters into 1 plus, what is the steel one? 1.2 into 10 to the power minus 5. 1.2 into 10 to the power minus 5 into what is the change in temperature? Original steel is calibration was done at 20. Now you are operating it at 40. So 40 minus 20, which is going to be how much? 20. So now you only tell me it is going to be 20 centimeters into 1 plus 1.2, 2.4. So you can say 0.00024. So you can say that it is going to be 20.00048. 48, but I have one doubt with the 0. So 20 into 1.00024 is 20.0048. 0048. This is the problem, man. This much length will be read as 20 centimeters. Real 20.0048 centimeters will be read as 20 centimeters. So more length will be read as less length. So this length whatever I have drawn is 20.0048. That much is read as 20. Sanjay. We will read it as 20 only. Reading is going to be 20, but the problem is we are reading more length, more actual length will be read as 20. Readings are, yes, I understood what you meant, Sanjay. True, correct. Okay. After this, I'll give you a break, man. Because a lot of logical thing I have done in this class. After this, I'll give you a break. After the thermal expansion in bodies with cavity. First, what I will do is, I won't directly jump into cavity. Let me explain ring and then disc. Then I'll relate to the cavity. It's going to be damn good. Look, man, we have a ring. And the radius of this ring is R, and when it is at some temperature T. When it is at some temperature T. Now what I will do is, I will increase the temperature of the ring. Then automatically the ring should expand or not? Obviously. So the ring has expanded. Now the final radius, whatever is there, let us take the final radius to be some R final. And what is the temperature of this one? The temperature of this one is some T plus delta T. I want to relate the final radius to the initial radius. Man, I don't know how to relate the radius, but I know how to relate the length. Linear expansion, na? Oh, my Jahnavi is saying, sir, your playlist is not visible properly. I'll contact them. I'll make sure it is going to get rectified by tomorrow, by end of the day. By tomorrow, end of the day. Huh? Okay, fine. Now look. Man, what is the initial length? 2 pi r. What is the final length? 2 pi rf. Okay. The length of it will change. So the final length is going to be the initial length into 1 plus alpha delta t. What is the final length? 2 pi rf. What is the initial length? 2 pi r into 1 plus alpha delta t. So from next time onwards, if they are going to talk about what will happen to the radius of the ring, you say confidently that this will be the radius of the ring. I proved it. You don't need to go step by step from next time. You don't need to go step by step from next time. I have clearly done it. Okay. Sir, you have kept a heading saying that thermal expansion in bodies with cavity, and you are talking about ring. Just 2 more minutes. Be patient. 2 more minutes. 2 more minutes. Now I am talking about disk. You should feel that we are talking about disk, right? Okay. Disk. This disk, I don't know whether you will be able to see the white. Yes. Has radius capital R. And this disk is at temperature T. Now, what I am going to do is, sir, Pragya Pinninti, which language you belong to, like which state you belong to, based on that I can suggest. You have to definitely learn differentiation and integration if you are going to be going into 11th, if you are in your first year, because differentiation integration plays a lot of role in physics. If you are going to be, your mother tongue is going to be Telugu, then in the Telugu channel, in Vedantu Telugu JEE channel, I have done all basics properly, including how to take elements. I have done basics, differentiation, integration, all of them properly, even graphs, everything I have done. And then I also taught something called as how to take elements for rod at a distance x dx, for ring at an angle theta d theta, why we have to take that elements. All those things have been properly explained. Yes, Pragna, then you can search in something called as Infinity. In Infinity, which has been done in the month of July. I have done basic maths. You can check from that Vedanta Telugu JEE. There is a playlist called as Infinity. Only Infinity. In fact, no one on YouTube has done how to take elements. I have done it. No one on YouTube has taught how to take elements. And because of that, many people struggle. Center of mass is difficult because That's when the integration starts. That's when people start saying at a distance x dx, at an angle theta d theta, at a distance r dr thick ring. All those things start from center of mass. That's why people find it difficult. But me, I teach it way back such that people are going to be conceptually strong, and by the time they are going to come to center of mass, they know how to deal with the things. Okay, fine. Now, man, I need relation between the final radius and the initial radius. Here we are talking about disk, which has area. So the final area is going to be the initial area into 1 plus beta delta t. Final area pi r final square. Initial area pi r square into 1 plus beta delta t. Pi can be cancelled out. R final is going to be R initial into 1 plus beta delta t to the power 1 by 2. Binomial approximation, beta delta t is small. If beta delta t is going to be small, I can use binomial approximation. So R final is R into 1 plus half beta delta t. For your kind information, beta is 2 alpha. Na? Beta is 2 alpha. So 2 alpha by 2 will be what? Alpha. So the final radius is R into 1 plus alpha delta t. Why? Because the beta is 2 alpha. Man, is there anything interesting with this result? Yes. Yes, there is interesting with this result. What is it? How the ring has expanded, disk also expanded in the same way or not? What is the difference between disk and ring? Man, disk has material spread throughout its area, but ring has material only on this perimeter or circumference. Now I am going to come to the cavity. Can I call disk and can I relate disk to ring? Yes. What is ring? Ring is disk with cavity or not. What I'll do is I'll take a knife, I'll just carve out this whole section, whatever is there, I'll just carve it out. I'll take it out. If I am going to carve out a portion of the disk whose radius is almost equal to capital R, then it will become a ring or not. So basically ring is nothing but what? Disk with cavity. Ring is nothing but disk with cavity. So now look, man, how disk with cavity, that is ring, is behaving. The complete disk also is behaving in the same way or not? Complete disk, and no longer I am going to call this as ring, man. No longer I am going to call this as ring. I am going to call the ring as disk with cavity. So how the disk has behaved, disk with cavity also behaved in the same way or not? Yes. That means whether there is material here or not, it doesn't matter. If material is going to be present over here, how the body would have expanded, in the same way the cavity also expanded or not? So cavity expands, cavity expands the same way as if material is present over there. As if material is present over there. So if material is going to be present, how the material will expand? In the same way, the cavity also expands. Ring can be treated as disk with cavity. Okay, nice, good. Sir, We understood. We understood. But is there a shortcut? Yes. Shortcut. For all these things, I'll give you shortcut. The shortcut is expansion of cavity or cavities is just like photographic is just like photographic enlargement. So this is a shortcut. It's a trick to directly get to the answer. But reality, the proper concept is this. If you have material, how it is going to expand? The body with the cavity. If material is absent also, it is expanding in the same way. So wherever material is missing, if you fill the material back, how the whole body will expand? Even the body with cavity also will expand in the same way. That is proper concept, which I proved now. Shortcut is this. Sir, I didn't understand what is photographic enlargement. I will explain you. For example, what you do is, you just take a ring. But what happened is that a portion of the ring is missing. A portion of the ring is missing. And that length, whatever is missing, is some L. So as temperature increases, what happens to L? What happens to L? As temperature increases, what happens to L? Comment. As temperature increases, what happens to L? Come on, comment. I'm waiting for your comment. I'm waiting for you. Come on. No, Akhil. No, calorimetry is going to start. Actually, I have to do I'll just complete thermal expansion of solids, then liquids, then gases. So thermal expansion of liquids some 15 minutes, thermal expansion of gases 5 minutes, then heat and calorimetry will start. Roughly in half an hour we are going to start. So some people have said it is going to increase, some have said that it is going to decrease. What majority of the people, in fact, when I was a student, my visualization was good, and because of that visualization, I suffered. What I thought was that, yes, as temperature increases, as the whole ring is going to expand, from this side, it will expand to this side, from this side, it will expand to this side. As a result, the gap will decrease is what I thought, right? But the answer is L increases. But the answer is L increases. That's the answer. Why? Look, I'll explain conceptually and with the help of shortcut also. Bodies with cavity, how they are going to be expanding. If material is going to present over there, how the material will expand, cavity also will expand in the same way. So now what you do is, you feel that there is material over here. You just take that, you have material here. If you have material here, as temperature increases, that material should also expand, right? Then cavity should also expand. If you have material over here, as temperature increases, it should expand. So L should also expand. That is one way, the conceptual way. Other is photographic enlargement. What you have to do is, we will just take a picture of it. I am taking a picture. Okay, I am taking a picture. I have taken a picture. You people can see. I have taken a picture. Oh, it's not properly focusing. Right? Focus, please. No, it's not auto focusing. Now, roughly you people can see. Look, What is photographic enlargement? Enlargement is nothing but zooming in. If you zoom in on this photo, can you clearly see that the gap is increasing, gap is becoming bigger? Previously it was small. Now if I zoom in, is the gap becoming bigger? Yes. So the shortcut for all these questions is going to be, whenever you are going to talk about thermal expansions, they are just photographic enlargements. Photographic enlargement is nothing but zoom in. You take a picture of this and you zoom in. So now I'll show you. I'm zooming in. Oh, shit. I messed it up. Okay. Arre, what happened, man? Okay, leave it. I'm not able to show it, but I hope every one of you have understood what I mean to say. Take a picture of this, zoom in. Whatever happens, the same is going to be happening to the cavity when you increase the temperature. Now, answer this. Answer this. A triangular plate has two cavities. One is square. One is square. One is square. So my suggestion to you is that this is A and this is also A, square, right? And the other is rectangular. One is A, other is B, and this gap whatever is there is X. Now they are saying the plate is heated. So what will happen to the A value and X value? What will happen to the A value and X value? Ram Pranav, I didn't get you, man. What you are typing, sir? I got 132 out of 140 in maths. Are you talking about like I don't know where 140 is going to be the marks? Like which examination you are talking about, Ram Pranav? You have to be clear on that. So the answer for this is all of them will increase. Why? You take a picture of this, man. You take a picture of this, and then when you zoom in, the square becomes bigger, rectangle becomes bigger, and even the x also will become bigger. That's it. All of them will expand. All of them will expand. Okay. Okay, I'm going to give a 10 minutes of break for you. 10 minutes of break. 10 minutes of break. Then after coming back, I'll do thermal stress. Right now it's 7:32. We'll be back. We'll be back at 7:43 p.m. We'll be back at 7:43 p.m. You people also please relax a bit, right? Have some water. If you can take some snacks or if you want to take some dinner, have it so that the next part is going to be done thoroughly. Okay. I'm back. Okay. So what is this thermal stress? Based on this also, you will get a lot of questions, man. Based on this also, you'll get a lot of questions. Generally, this is the one which is going to be combining mechanical properties of solids with thermal properties. So now look, for example, let us just take that these are two walls. Between these two walls, we have a rod which is fixed. A rod which is fixed. The length of the rod is L here. Length of the rod is L here. And this rod is at temperature T. Now, when you increase the temperature, that rod wants to be at some length. But these walls won't allow it to expand. So let me draw it separately. See, at temperature T, length is L. Now, at delta T plus delta T temperature, at T plus delta T temperature, at a temperature of T plus delta T, this particular rod wants to be at L into 1 plus alpha delta T length. At this much length it wants to be. This rod wants to be at this length, but what the walls have done, they applied a force, and you can say that they have compressed it to L length. So the rod which wants to be at this much length, the walls didn't allow it to go to that length. That means the walls have applied force, and you can say the walls have compressed this rod to L length. Normally, at T plus delta T wants to be at this length, but walls have compressed it to this length. Okay, what is Young's modulus? So the Young's modulus is going to be stress divided by the strain. What is stress? The restoring force developed in the rod per unit area, and at equilibrium, restoring force developed inside the rod is equal to the force you have applied. Here you are not applying. My intention of saying you have applied is the walls have applied. If the temperature is increased by delta T, walls are applying this F force and making sure that the length will remain L. So stress is going to be whatever the force the walls have applied divided by A. Now, strain, change in length by original length. It wants to be at this length. So the original length is this and it is at this length. So what is the change? Can I say the change in length to be L alpha delta T divided by what is the original length? Man, this is the original length which is not clearly mentioned in the books. But JEE Advanced will test your conceptual clarity. Rod wants to be at this length. This is the original length of the rod at a T plus delta T temperature, but the walls have compressed it to L length. Majority of the people will think that the original length is L. No, the original length of the rod at T plus delta T temperature is L into 1 plus alpha delta T. This conceptual clarity is missing from students. Okay, fine. This F by A is what we call as stress, right? So I can write Young's modulus as stress, right? That is nothing but due to the increase in temperature. That's why I will call it as a stress which developed because of increase in temperature. That's why I call it as thermal stress. Divided by what is the change in length? L alpha delta T. By what is the original length? L into 1 plus alpha delta T. So from here, I can write the thermal stress as what? So the thermal stress that developed is going to be what? Young's modulus into L alpha delta T by L into 1 plus alpha delta T. For your kind information, alpha delta T is very small or not. So I can roughly say this to be L. So for calculation purpose, for calculations, we can say thermal stress, we can say the thermal stress developed is roughly equal to Y. See, if you write this as L, this L and this L is going to get cancelled out. So it is going to be Young's modulus alpha into delta T. Young's modulus alpha into delta T. Okay, now do a question. 2019 JEE mains. 2019 JEE mains. A rod of length capital L at room temperature and uniform area of cross section A is made of metal having coefficient of linear expansion alpha. It is observed that an external compressive force F is applied on each of its ends, prevents any change in the length of the rod when the temperature rises by delta T. The Young's modulus for this metal is, man, Young's modulus is going to be what? Stress divided by strain, right? Now that Young's modulus, stress can be written as what? Whatever the external force you have applied per unit area, ultimately at equilibrium. Actually stress should be written as restoring force developed per unit area. That restoring force will be equal to the external force applied at equilibrium. Now strain is going to be what? Change in length by original length. It wants to expand, but it is not allowed to expand. So it is similar to this case or not? Similar to this case, right? So what is the change in length? L alpha delta T by original length, L into 1 plus alpha delta T, but can be roughly written as L. So I can write change in length L alpha delta T by original length, which is going to be roughly L. So the Young's modulus can be written as F by A by LL gets cancelled out, alpha delta T. So we can write the Young's modulus to be F by A alpha delta T. F by A alpha delta T. Okay, super. Done. We are done with thermal expansion of solids. And as I said, majority of the times questions are going to be coming from thermal expansion of solids only. Rarely you are going to get questions on thermal expansion of liquids. But keep one thing in mind. When I am going to talk about liquids and when I am going to be talking about gases, there won't be coefficient of linear expansion, there won't be coefficient of areal expansion, there will be only coefficient of volume expansion, because fluids occupy volume. Fluids occupy volume. So directly we are going to talk about coefficient of volume expansion for these things. Coefficient of volume expansion for these things. And it is going to be what? Gamma. Okay. Same story, man. The same story. Gamma. Fractional change in volume per unit change in temperature is going to be constant for liquids, but it won't be constant for gases. It is going to be changing. That we will talk about. But for solids and liquids, the coefficients of thermal expansion, whatever will be there, they are roughly constant. Okay. Now the change in volume can be written as V gamma delta T. So the final volume is going to be initial volume into 1 plus gamma delta T. Man, but whenever we are going to talk about liquids, if the volume is going to be changing, its density is going to be getting affected. And the gamma, when compared with solids, gamma of liquids will be slightly greater. Slightly greater. Okay. So how the density is getting affected? How the density is going to get affected? Right? So if I am going to talk about mass, mass is going to be constant, right? So mass can be written as initial volume into density is going to be final volume into the final density. So the final density is going to be V rho by V final. So we already know the V final, which is going to be V into 1 plus gamma delta T. So the V and V are going to get cancelled out. So the final density is going to be initial density by 1 plus gamma delta T. So this is how the variation in density is going to be there. And majority of the times I have seen some good questions to be asked on this rather than this. If you are operating at less temperature, I don't remember. I think the question Mr. Muhammad is asking, sir, previous steel question. So the reading will be read as too short or long. Actually, if you are operating at less temperature than the calibrated one, it will be read as less one will be read as bigger, right? Right? Too long. Smaller will be measured as more, too long. Okay, good, Prasanna Kumar. Okay, fine, but we have a challenge, man. We have a challenge. Because all these fluids, they are going to be filled in a container. So what is the actual expansion and what we feel are two different things. What we feel is apparent. Whenever our feelings are taken into consideration, we call it as apparent. So to explain that apparent, what we feel, for example, we have a container, right? And this container, let's say, is at 30 degrees Celsius, and at this situation, we have liquid which has filled the whole complete container. Liquid has filled the complete container, and at 30 degrees, let's take the volume of the container to be some 10 liters. Then volume of the liquid is also going to be obviously 10 liters. Now what I'll do is, I will increase the temperature to some 50 degrees. If I increase the temperature to 50 degrees, definitely the volume of the container will increase. Temperature, I'll take it to be 50 degrees. Temperature, I'll take it to be 50 degrees. And for you to understand, I am taking that the liquid at 50 degrees also is completely filling the container. No overflow, nothing short of the brim. Exactly filling the container. Then if you talk about volume of the container, let us say some 13 liters, then automatically the new volume of the liquid is also what? 13 liters. So if you are going to talk about actually volume of liquid increased by 3 liters. But what I feel that previously liquid is filling complete container, now also it is completely filling the container. That means there is no change in the volume. What I feel is that volume of liquid didn't change. So my feeling is apparent, man. Whatever our feelings are going to be there, we call them as apparents. Previously also liquid is completely filling, now also liquid is completely filling. That means the level of the liquid didn't change in the container. That means the volume of the liquid hasn't changed. That's what I feel, but reality is different. So whatever we feel are going to be called as apparent. So how to get the apparent? Apparent change in the volume The apparent change in the volume is going to be the real change in the volume minus the change in volume of the container. So in the previous situation, what has happened? Liquid changed by 3 liters, container also changed by 3 liters. That's why you're not feeling that the liquid has changed its volume. From where I am copying, sir? Sir, your lectures are copying. From whom I am copying? I copy from myself. If exact data is going to be, if exact the same thing is going to be there somewhere on YouTube, not done by me, done by someone else, tell me, I'll resign now itself. I don't see anyone. I have my own way of teaching. I'll just do that. Krishna Pardu, if you can prove, I'll just resign and leave. I don't even see anyone. I make my own lectures. Yes, I copy from myself. Let's say, for example, if I have done this topic in Vedanta Telugu JEE, then similar slides or same slides also. If I feel that I don't need to add anything, then I'll do the same thing. Or if I have done something in Vedanta JEE English, then the very same me might do similar content on Telugu JEE. But I won't copy from anyone. Okay, leave it. I don't mind the comments. Apparent. So I can write V gamma apparent into delta T is going to be real. V gamma real into delta T, V gamma of the container into delta T. Then the apparent gamma can be written as the real gamma of the liquid minus the gamma of the container. But for all these questions, whenever these apparent changes are going to be there, oh, my lectures are being copied, Krishna, then it's up to them. Okay. Don't mug up formula. Don't mug this formula up. Always, I believe in one thing, right? Understand the concept, use your common sense, solve the question. I have taken up a question. Do it. Do it. It's a good question. It's a good question. Arey, Darshan, alternating current is going to be taken by Shreyas sir because he is the one who has completed EMI and he is going to be the one who is going to be doing AC. So whatever the topics are going to be said to me by him, I am just doing those topics because he is the one who started the Roar series. He knows what he has done, right? So what he does generally on Saturdays, he is going to give me, okay, Madhan sir, these are the topics which are not done. Can you please do these topics? So this week he said, okay, in one lecture complete thermal physics, in one lecture do heat transfer. Madhan, I don't know Tamil, man. Although my wife knows Tamil, but I don't know Tamil. I am unique. See, that's what, man. So if someone is trying to copy someone else, then you're not going to be unique. You have your own way of understanding things. I believe in that. Never I have watched any YouTube video. Never. If I have a problem, I'll Google. If I have a problem, conceptual understanding, if I have a problem, then I'll try to Google for some research papers. I'll read through the research papers and I'll understand the theory on my own. On my own. Everyone is unique. If I make you people who are learning from me to teach, you have your own way of explaining things because you have understood in your own way. Superstar Rajnikant. Wow. Sir, please make more PYQ sessions. We will be doing it, ma'am. We'll be doing it. Last topics, whatever were given to me, they are very small. As a result, I have put the PYQs in the class itself. But for this, heat transfer and this one together, there will be a PYQ session. Who is that, Krishna? Krishna, who is that who is copying? Let me know the name. A bakelite beaker has volume capacity 500 cc at 30 degrees Celsius. When it is partially filled with VM volume at 30 degrees of mercury, it is found that the unfilled volume of the beaker remains constant as temperature is varied. right? Gamma of the beaker is given, gamma of the mercury is given, and what they are asking is the Vm is close to, that is how much volume is partially filled. Okay, okay, okay. Now look. Let us take that this is mercury and the volume of mercury, let us take it to be Vm. The whole container is, let us take it to be Vc. Then what is the empty space, man? This empty space, whatever is there, this empty space, whatever is there, is going to be Vc minus Vm. They are saying that that empty space is constant, it seems. Okay, look, this at 30 degrees, right? Now whatever might be the temperature, this empty space is remaining as it is. So let us draw one more diagram. So the container size will increase as temperature increases, and at the same time even the volume of the mercury is going to be increasing. Right? So I will write this as Vm dash, and the total volume of the container is going to be some Vc dash, because volume of container also will change. So now what will be this free space? This free space is going to be Vc dash minus Vm dash. That's it. Now whatever is given in the question, I'll use that. Okay, now what did they give? They said that the Vc dash minus Vm dash, that is the empty space, is remaining as it is. Is what they said. Okay, fine. What is the Vc dash? Initial volume of the container into 1 plus gamma c of the container into delta T minus Vm into 1 plus gamma of the mercury into delta T is going to be Vc minus Vm. Okay, fine. Now Vc gamma c minus Vm gamma m into delta T should be equal to 0. I skipped one step in calculation. So Vc, which is 500, into gamma c. What is the gamma of the bakelite container beaker? 6 into 10 to the power minus 6. 6 into 10 to the power minus 6 minus volume of mercury multiplied with gamma of mercury, 1.5 into 10 to the power minus 4. 1.5 into 10 to the power minus 4 should be equal to how much? 0. So what will be the Vm value? It is going to be 5 into 6 into 10 to the power minus 4 by 1.5 into 10 to the power minus 4. As a result, you get it to be 20 cc, because this is going to be 6 by 1.5 is 4, 5 into 4 is 20. So if the volume of the mercury that is filled in the container is going to be 20 cc, then as the temperature keeps changing, the free volume is going to be kept constant. You can, Mohammed, I think you can. Okay. So this is how you have to think of, for the liquids. Even expansion of container should be there behind in your mind. When you are thinking about questions on liquid, even expansions of container should be there. Now, anomalous behavior of water. Generally, what should happen, man? If temperature increases, volume should increase. But water is different. And it is because of that only the marine life is surviving. But I don't want to waste time in explaining the marine life and all those things, how it is surviving and all that stuff. Just keep this in mind that, okay, because of this anomalous behavior of water, the marine life is surviving. That's it. What will happen as temperature increases? Generally volume should increase, but water behaves in a different way. Volume decreases till what point of time? 4 degrees. Even though as the temperature is increasing, volume is going to be decreasing for water. Now, if volume is going to be decreasing, obviously what should happen to density? If volume decreases for the same mass, if volume is going to be decreasing, automatically what should happen to the density? It should increase. So the density of water is maximum at 4 degrees Celsius. Is maximum at 4 degrees Celsius. It behaves exactly in the reverse way. Okay, I am not able to resist myself. I will explain how the marine life is surviving, man. That's how I am. I can't stop. Okay, look, let us take this whole lake is at some 5 degrees Celsius, and the surrounding temperature is some minus 10 degrees Celsius. So who is going to cool down first? Obviously the layer which is going to be open to the atmosphere. So this is going to cool. So if this is going to cool, then what will happen? 5 degrees, right? If it is going to cool from 5 degrees, if it is going to go down, its volume will go down. That means its density will increase. As a result, this layer which is cooled goes down. So the new layer will expose. A new layer will expose to that. Even that new layer will also get cooled down, goes down. Like that, all the layers will expose, and the temperature of the lake starts going down to what? Lower temperatures. Then finally, let's take the whole lake, let's say, has come to 4 degrees Celsius. When the whole lake has come to 4 degrees Celsius, the surrounding temperature is minus 10 degrees. Now one beautiful thing happens. What is that? This layer which is exposed, its temperature has to go down. As the temperature goes down, normally volume should go down, but here volume won't go down, volume will increase. As a result, density will decrease. That means the lighter, denser one is going to stay there. So from 4 degrees, this layer will become 3 degrees, will become 2 degrees, will become 1 degree, will become 0 degree, and then it starts freezing. So freezing is taking place from the top, and below is what? Water, and it is in liquid state. If it is in liquid state, all the fish that is going to be there over here, as it is water, and that water is going to be at higher temperature also, so the fish is able to survive. So the freezing is not happening from the bottom, freezing is happening from the top. Why? It is because of the anomalous behavior of water. Once the water reaches 4 degrees, from there if you are trying to freeze it, its volume, instead of decreasing, its volume will increase. As a result, density will decrease. If density is decreasing, that layer will remain there only, it won't go down. Higher denser ones should be at the bottom. That's how the freezing starts from the top in water. As a result, the marine life survives. In all other liquids, freezing will start from the bottom, but for water, freezing will start from the top. Okay, next, gases. Man, coefficient of volume expansion for gas is not a constant. gases are different from the solids and the liquids. So if I am going to talk about coefficient of volume expansion for gases, we should not talk about big changes because gamma is a variable. Whenever variables are going to be there, we have to talk about small changes. So the gamma for gas should be written as small changes, small fractional change in volume for small change in temperatures. This is what is the gamma. So if I am going to be talking about, let's say, isobaric process. So what is the gamma of the gas undergoing isobaric process? And in detail, the thermal behaviors or the gases we will talk about in Cartesian thermodynamics. I hope Cartesian thermodynamics is also done to you. Look, PV is equal to nRT is the ideal gas equation and P is constant. Our aim is to get dV. That means we have to differentiate. As P is a constant, we don't need to differentiate P, nR dt, right? So from here, I can get dV by dt is going to be what? nR by P, man. Now look, if I want gamma, there should be V in the denominator. So what I will do is, I'll just multiply with this. And now this left side one can be written as what? Gamma, and this is nR by PV, man. PV can be written as what? nRT. So what is the coefficient of volume expansion for isobaric process? It is 1 by T. Now tell me, in isobaric process, will the temperature change? Yes. If temperature is changing, is the gamma continuously changing? Yes. So for gases, coefficient of volume expansion continuously changes, and it is also going to depend on the process. Depending on the process, you better use this. That's it. Now they are going to ask, what is the coefficient of volume expansion for a gas undergoing adiabatic expansion? Okay. Find gamma of gas for adiabatic. See, whenever you want to calculate the coefficient of volume expansion, it is going to be this, which is going to be helping you. So your aim is to calculate this. Keep that in mind. Okay. Now, process. PV to the power gamma is going to be what? Constant. Or we need dV, V's and T's, right? So I will take T V to the power gamma minus 1 to be constant. This is the adiabatic process. Now if I differentiate, first T will be differentiated, V to the power gamma minus 1. Then T will be kept as it is. We have to differentiate V to the power gamma minus 1, which is going to be, this gamma and this gamma, you will get confused. This gamma is small, like this gamma is going to be that Cp by Cv. This gamma is coefficient of volume expansion. V to the power gamma minus 2 into dV is going to come out to be how much? 0. So I can write dt into V to the power gamma minus 2 into V plus gamma minus 1 into T V to the power gamma minus 2 into dV is going to be 0. So from here, this and this can be cancelled out, and we can write dV by V dt to be equal to minus 1 by gamma minus 1 into T, where this gamma is Cp by Cv, where this gamma is Cp by Cv. Just keep that in mind. So they can give any process, man. They can give any process. If you want coefficient of volume expansion, this is what you have to do if they are talking about gases. That's it. We are done. We are moving to the last part, heat and calorimetry. Man, what is heat? Heat is a form of energy. So what happens when you give heat to a body? What happens when you give heat to a body? Either the body is going to be changing its state or it is going to be increasing its temperature. Right? So I need to define few terms. Before we start dealing with this part, heat and calorimetry part. And I am going to give you one blind method. There are many people who struggle every year. They are going to say 1 gram of ice is mixed with 1 gram of steam. They don't know how to start. People have problem with starting the question. If they start the question, they'll get the answer. That's why to make you start the question, I have a blind method for you. No, not 2 more hours. Like 1 more hour, that's it. 1 more hour max. Okay, fine. Specific heat. I don't think it will take even 1 more hour also. Because Newton's law of cooling is deleted. We don't have Newton's law of cooling. So I have to just define these terms and I'll move on. Specific heat is the amount of heat you have to give per unit mass to change its temperature by 1 Kelvin. Amount of heat per unit mass per unit change in temperature. So the delta Q can be written as ms delta T. Now look, I am not going to talk about molar heat capacity here, right? In this chapter it won't be useful. In KTG it will be useful. Whatever are useful over here, those only I'll do here. Now look, one more thing which is going to be very much useful is going to be thermal capacity, which is going to be represented with capital S. How is capital S defined? It is going to be like the amount of heat you have to give per unit change in temperature to the body. So it is not per unit mass, it is just for the body. So delta Q, the amount of heat you have to give to create unit change in temperature for a body. So from here, the delta Q is going to be S, capital S into delta T. So if you are going to be comparing these two, how to get the thermal capacity of a body, it is going to be mass of the body into specific heat. And for your kind information, we are going to be using few things. Specific heat of water is 1 calorie per gram per cc. Oh, sorry, not cc. 1 calorie per gram per Kelvin. And specific heat of ice is going to be half calorie per gram per Kelvin. So generally, whenever we talk about heat, we are going to talk in terms of calories, right? So then what is the definition of a calorie? Look, I have taken first of all specific heat of water to be 1 calorie per gram per Kelvin, but the specific heat slightly changes with the temperature. Specific heat slightly changes with the temperature. Specific heat is almost constant. Specific heat is almost constant for solids and liquids. For solids and liquids. If I am going to talk about water, look. The specific heat of water at different temperatures, if I am going to see, the graph is going to be like this, man. Look, you can see the minimum bar at 14.5 degrees Celsius. So if you are going to talk about, if you take this to be 1 calorie, if you are going to be talking about at 100 degrees, it is going to be 1.008 calories. And if you are going to talk about at 0 degrees, it is 1.006 calories. Now look, roughly can I say the specific heat of water, irrespective of temperature, to be roughly 1 calorie or not? Roughly 1 calorie, but not exactly 1 calorie. That's why they have given the definition. What is 1 calorie? 1 calorie of heat is the heat required to change 1 gram of water, 1 gram of water to change temperature, of 1 gram of water from 14.5 degrees Celsius to 15.5 degrees Celsius. To take water's temperature from 14.5 to 15.5, how much ever heat you are giving, that much is defined as 1 calorie. That much is defined as 1 calorie. Okay, that much is defined as 1 calorie. Now look, as I said, different things have different temperatures. The water has different specific heat, but roughly we can take it to be constant. Okay, fine. Now we have the specific heat defined, we have the thermal capacity defined. As I already said to you, when we give heat, when we supply heat, a body will change its temperature or it is going to be changing its state. So roughly, if I am going to talk about what happens to the body as we keep supplying heat, look, on this side, heat, and if I am going to be talking about time, or not heat also, just a second, if I am going to take this to be temperature, first temperature keeps increasing, then for certain amount of time the temperature will be constant, again the temperature keeps increasing, again the temperature will be constant, and from here on things are going to be different. So look, this is the solid phase. So body takes heat, it is increasing its temperature, and then it is changing its state from solid to liquid. So change of state is happening over there, and then once it is going to completely turn to liquid, again the liquid's temperature is increasing. So here this is purely in the liquid form, and then this is the state where liquid is turning to gas. And after gas, we are not going to discuss about it. We will talk about in KTG and thermodynamics. Okay. Now, I have taken care of these temperature changes, but I haven't taken care of those situations where the state is changing. Temperature is constant, but you are supplying heat. But temperature is not changing. So that heat, whatever is taken, will be in the hidden form. Generally, what our common sense says is that if heat is given to a body, its temperature has to change. But whenever there is state change from solid to liquid or from liquid to gas, heat will be continuously taken, but its temperature won't change. So that heat, whatever is going to be taken, is not visible to us. That's why we call it as latent heat. So latent heat of fusion is going to be, for water, is going to be 80 calories per gram, and latent heat of vaporization is going to be 536 calories per gram. And how is latent heat defined? So the latent heat is defined as the amount of heat you are supplying per unit mass to change its state. The amount of heat supplied per unit mass to change its state. So delta Q is going to be M into L. Delta Q is going to be M into L. Mr. Morax, if you can't take it, get out. Who is asking you to listen? I'm not here to dance, man. If you are not able to understand, get out. Or you listen to whomever you like is going to be teaching. Who is asking you to come? If you can't take it anymore, get out. Okay. These are a few things. Now, one more which is very important while solving questions. One more thing which is important, while solving questions, is water equivalent. While solving questions, this is going to be very useful, man. Because they're going to say water equivalent of a body is this much. What they are trying to say is that you can replace that body with that much quantity of water. For example, I am Madhan. See, let's take me. I'm putting it in layman terms. Madhan. My body's water equivalent they have given. My body's water equivalent is given as, let's say, 10 grams. Let's say 10 gram. That means while solving questions, my body can be replaced with 10 grams of water. So basically, what it means, I'll tell you. Let's say you have to supply delta Q amount of heat to increase my temperature by delta T. Then even 10 grams of water, if the same delta Q, how much ever is given to my body, if the same heat is given to 10 grams of water, even its temperature will change by the same amount. So if you look at from the heat perspective, my body and 10 grams of water are equal. My body and 10 grams of water are equal. That's what is called as water equivalent. So from next time onwards, whenever you are going to come across a question where they say water equivalent of the body is 20 grams, you just forget about the body, treat it as 20 grams of water as far as heat is concerned, right? As far as heat is concerned. Okay, fine. Then formula wise, how it is going to look like? Okay, this delta Q for the man can be written as heat capacity of the person multiplied with the delta T. And if you are going to talk about water, delta Q is going to be mass of water, specific heat of water into delta T. So if you are going to equate, then the thermal capacity is going to be mass of water and specific heat of water. If you put specific heat of water as 1, if SW is going to be put as 1 calorie per gram per Kelvin, if you put SW as 1, then numerically thermal capacity is equal to MW. Thermal capacity will be equal to, so from this, capital S is going to be MW. Numerically, water equivalent is equal to thermal capacity of body. But keep in mind thermal capacity of the body. But keep in mind that thermal capacity should be put in calories. Why? Because I have taken in the RHS calories, so LHS should also have calories. This much is enough. We can solve the questions. This much is enough to solve the questions. Capital S is thermal capacity. I have explained. I have already explained. Thermal capacity is capital S. What is capital S? The amount of heat you have to supply to the body to change its temperature by 1 Kelvin. So how much our heat you have to supply to the body to change its temperature by 1 Kelvin is going to be called as thermal capacity of that body. Is called as thermal capacity of that body. Now did you understand Angel's miracle? I hope now you understood. Okay, fine. Sanjay, I'll be cool, man. But see, generally I have to take some 3 hours of session. Already 3 hours is done. I'm putting a lot of effort and that fellow is coming and talking some random shit. Obviously. Okay, fine. The core part and the important part has come. The core part and the important part has come where many people are going to struggle. Right? Law of mixture. What is that? You are going to be combining 1 gram of ice with 1 gram of steam. So for calculation purpose, please take latent heat of fusion to be 8 calories per gram and latent heat of vaporization to be 540. Just for easy calculations, nothing else. Actually, latent heat of vaporization is 536. And let me spend some time with this one. Look, if you want to melt 1 gram of ice to 1 gram of water at 0 degrees, you have to supply 8 to the ice. 80 to the ice. 80 to the ice. Okay. Now, if water at 0 degrees, if it is getting converted to ice at 0 degrees, for every gram of water converting from 0 degrees to ice at 0 degrees, it will release 80 calories. Now, water at 100 degrees, if it is getting converted to steam, for every gram of water converting to steam, you need to supply 540. If 1 gram of steam gets converted to 1 gram of water, then steam gives away 540. So keep that in mind. That much common sense you should have. And one more thing, what is the law of mixtures? Is that I am assuming no heat is lost or no heat is taken from surroundings. So when I am going to talk about law of mixtures, What is the assumption? What is the assumption? The assumption is going to be no heat is exchanged, no heat is exchanged with surroundings. That means if I am combining ice with hot water and ice will exchange heat, that's it. No heat will be lost to the surroundings, no heat will be absorbed from the surroundings, keep that in mind. Okay, what is the law of mixtures? It is going to be heat lost by hot body is going to be heat gained by the cold body. Heat gained by the cold body. And for your kind information, this has come from conservation of energy only. Hot body will lose heat, cold body will gain it, and ultimately when hot body loses it, it will cool down, and when the cold body gets that heat, it will heat up, and at equilibrium, both the bodies at equilibrium, all the bodies involved should have same temperature. All the bodies involved should have same temperature for sure. Now you might have a doubt. Sir, if I have 1 gram of water at 0 degrees and 1 gram of ice at 0 degrees, will they exchange heat? No. 1 gram of water at 0, 1 gram of ice at 0, they won't exchange heat. 1 gram of steam at 100 degrees, 1 gram of water at 100 degrees, will they exchange heat? No. If there is no temperature difference, no heat exchanged. No heat will be exchanged. Okay, fine. Now look, how do we solve all the questions on mixtures? I will give you one blind method. Because majority of the students have problem. Majority of students have problems starting the question. So the blind method which I would like to give you is that, especially for those who have a starting problem, assume everything to be water at T degrees Celsius at equilibrium. You start taking this assumption. If you start with this assumption, things will become easier. At least you will start the question. Once you start the question, I know how to give answer to you with this blind method. Yes, heat will be conserved. Okay. Now look, man, the question which I am giving to you is that 1 gram of steam which is at 100 degrees Celsius is mixed with 1 gram of ice at 0 degrees Celsius. I want final temperature, and once equilibrium is attained, how much water is present. I want the final temperature, and I also want how much water will be present. Okay, man, who is going to be losing heat? Who is going to be losing heat here? Obviously, steam is going to lose. When the steam is going to be losing, how it is going to be losing? From steam, first it will become to water. Okay, fine. Let me write it. Heat lost on the left side, heat gain or heat gained on the right side. That's it. First of all, let us start. What we have, I said everything will become water at T degrees. So you have to write the steps up to everything at water at T degrees. Now this 1 gram of steam this 1 gram of steam, which is at 100 degrees Celsius, ultimately should become water at T degrees. Ultimately should become water at T degrees. That means to go to water at T degrees, first it should get converted to water. It will get converted to 1 gram of water at 540. So 1 into 540. So when steam gets converted to water at water at 100, it is releasing 540. Next, how much heat is released when it is losing temperature? When temperature is going to be lost, now you have to use ms delta T. M1, water, specific heat, 1. What is the change in temperature? I should write 100 minus T, not T minus 100. Why? We are talking about heat lost. Already we have taken the negative sign into consideration, so we just need magnitude. So this much heat is lost. Mohammed, sir, how to understand which substance have heat loss and heat gain? Hot ones will lose the heat, cold ones will gain the heat. That's it. So whichever is at higher temperature is the one which is going to be losing heat. Whichever is at lower temperature, that's the one which is going to be gaining heat. Okay, fine. Now look here. We have ice at 0 degrees. As I said, I have an assumption that everything got converted to water at T degrees. That means even this 1 gram of ice also should convert into water, right? So first that 1 gram of ice should become water. That means it should change its state. 1 gram of water at 0 degrees Celsius. Then it will go to where 1 gram of water finally T degrees Celsius. So here there is change of state. If there is change of state, which formula we have to use? Delta Q is M into L. What is M? 1. What is L? As it is going to be ice to water 80. Now here delta Q, it's change in temperature. So I have to use ms delta T. So what is M? 1. What is S? 1. Delta T, it's T. Now heat loss should be equated to heat gain. Now is it fine? Is the video fine for everyone? Is the video fine for everyone? Hope this is fine. Now heat lost. Heat loss is 540 plus 100 minus T. How much is the heat gain? 80 plus T. 80 plus T. Now you tell me 640 is going to be 80 plus 2T. So when I am going to talk about 2T, it is going to be 560. So the temperature is 280 degrees, man. The blind method will give you answer. The blind method will give you answer. Look, what did we assume in the blind method? We have taken everything to be water at T degrees. Now the T is coming out to be 280 degrees. Can water exist at 280? No, water won't exist at 280. Water won't exist at 280. Water can exist at 100, but not 280. That means the blind method is trying to tell us something. What is that something? Our assumption is wrong. Everything to be water at T degrees. Our assumption is wrong. Why? I'm getting it to be 280 degrees and water can't exist at 280. But still the blind method gives you answer. If in blind method, if T is more than 100 degrees Celsius, then the equilibrium temperature, directly you mark it to be 100 degrees Celsius. Reason is some steam will be left. Some steam will be left. Look, if the temperature is between 0 to 100 degrees, then no problem. Then there is no problem, everything is water. Then no problem, everything is water. Everything is water. If T is going to come out to be between 0 to 100, then your equilibrium temperature is whatever the T you have got. If the T is coming out to be less than 0 degrees, then the equilibrium temperature will be 0 degrees Celsius. Reason, some ice will be left. Some ice will be left. Man, if you are combining, let's say, some steam and ice, for example, if ice is left, ice is at what? 0 degrees. That means the rest, whatever is there, everything has come to 0 degrees. If ice is left, ice is at 0 degrees, then the equilibrium temperature is 0. If steam is left, steam is at 100 degrees. That means the other thing has come to 100 degrees. So with the blind method, you can directly find the equilibrium temperatures. With the blind method, you can directly get the equilibrium temperatures. That is the reason why some good competitive examinations, they won't ask the equilibrium temperature. They will ask how much quantity of water is present. Look, I got 280. If it is going to be more than 100 degrees, some steam will be left, right? So now I'll show you how to calculate the quantity of water. As the temperature came out to be more than 100, some steam will be left, right? Some steam will be left. If the temperature is more than 100, who is dominating? Means steam is dominating. So some steam will be left. That means the entire steam won't get converted. So you start the steps like this. And what is the equilibrium temperature? The equilibrium temperature from the shortcut, I gave it to you that it is, or from the blind method, equilibrium temperature is 100. Now look, man, 1 gram of steam won't be converting now, only X grams of steam. X grams of steam at 100 degrees Celsius will convert to X grams of water at 100 degrees Celsius. That's it. Now, on the other side, we have ice. 1 gram of ice, which is at 0 degrees Celsius, first should convert to 1 gram of water at 0 degrees Celsius. 1 gram of water at 0 degrees Celsius. Then it should go to 1 gram of water at 100 degrees Celsius. Why? The moment you get that the temperature is more than 100, the equilibrium temperature is 100. That means whatever are there should have temperature as 100. Okay. Okay. Now look. Let us find out how much heat here. M into L, which is going to be 1 into 18. How much here? Ms delta T. How much is M? 1. How much is S? 1. How much is the change in temperature? 100. Here X grams. Delta Q is M into L. X grams. So X into 540. So heat loss should be equated to heat gain. So 540 into X is the heat loss. What is the heat gain? 80 plus 100. So from here you get it to be 1 by 3 grams. So 1 by 3 grams of steam got converted to water, and 1 gram of ice also got converted to water. So finally, how much water is there? Finally we have 1 gram plus 1 by 3 grams of water. Sir, why did you write 1 gram and 1 by 3 grams separately? See, this 1 gram of water is because of melting of ice. This 1 by 3 grams of water is because of condensation of steam to water. That's it. This is the blind method, man. Valid everywhere. Valid everywhere. Any situation. If you are not able to start the question, done. Use the blind method. What is the blind method? I started with an assumption that everything is water at T degrees Celsius. I started with an assumption that everything is water. If my assumption is wrong, I'll get weird temperatures. From that weird temperatures also, I'll get information. What is that? If you solve this question, I got the temperature as 280 and water won't exist at 280. And if it is coming out to be too hot, too high temperature, that means steam is dominating. That means some steam is left. If I get the temperature to be negative, like minus 50, that means it is too less. Too less means some ice is dominating, right? Some ice will be left. That's it. Easily you can solve any of the questions. Easily you can solve any of the questions with this blind method. But I have a info which will help you. I have a info which is going to help you. What is that info which is going to help you? See, look, 1 gram of steam at 100 and 3 grams of ice at 0. If you mix them, then everything is water. Then everything is water at 100 degrees Celsius. Look at the ratio. If you put it in 3:1 ratio, then everything is going to be water at 100. Now, 1 gram of steam, if you are going to be clubbing it with 8 grams of ice, then everything is water at 0 degrees Celsius. If you know these results, it will save some time for you in calculation. For example, if the ratio is less than this, that is 3:1, what we did in the previous question, 1:1 we mixed, then steam will be dominating. Here 8 grams of ice with 1 gram of steam. If I club 1 gram of steam with 9 grams of ice, then ice will be dominating, some ice will be left. So if the ratio is between 3:1 and 8:1, it's fine, everything will be water. If the ratio is less than 3:1, steam will be left. If the ratio is more than 8:1, then some ice will be left. Clear, everyone? With this, you can save some time. But as I said, everyone has a starting problem. To help you with the starting problem, I have gone through this blind method. This is something which I have found out for myself. Why? To make sure that the average students and below average students also will start the question and will get the answer. Those who are above average and those who are good, they can directly use this data. So if the ratio is going to be less than this one, steam will be left. If the ratio is more than this one, ice will be left. That's it. Okay. Yes, if there is more ice, then it is going to be 0 degrees. If there is less ice in the sense, obviously not when compared with steam. Obviously, ice has more weight than the steam. So rather than memorizing like that, you better just have rough idea of this. That's it. Okay. Now, I would like to give you one small question. That is, I am clubbing the question is 1 gram of steam at 100 degrees Celsius with 1 gram of ice at minus 100 degrees Celsius. We are clubbing this. What I want you people to find is the equilibrium temperature. Find the temperature at equilibrium. Find the temperature at equilibrium. And information that is given is the specific heat of ice is half calorie per gram per Kelvin. And specific heat of water is 1 calorie per gram per Kelvin. 1 calorie per gram per Kelvin. Mr. Sanjay, what's the answer for this? Do you know why I have given this? There are many people who are going to mug this one up. See, this, whatever the statements I have given are going to be for ice which is taken at 0 degrees, man. So that is the reason why I don't like to mug up stuff. Better, I'll go with the blind method. Sir, when will you complete fluid mechanics? Whenever I am asked to do, I'll do it, man. But mostly, like, whenever I am going to be doing it in Vedantu Telugu JEE, more or less on the same, at the same time I'll try to do. I think I'll be doing fluid mechanics in December 3rd week for them. 200. Sultana, 200. No. You won't get 200. Come on. Heat lost and heat gain is what we have to talk about. Who is going to be losing heat? Obviously, the hot one is going to be losing heat. Who is going to gain? The cold one is going to be gaining, right? And we start with the blind method. What is blind method? The blind method is going to be everything water at T degrees. Everything is water at T degrees for the blind method. So start with it. 1 gram of steam, whatever is there, right, should get converted to first 1 gram of water at 100. Then it should become 1 gram of water at T degrees. 1 gram of water at T degrees. Why 1 gram of water at T degrees? In blind method, we will take that everything got converted to water at T degrees. At equilibrium, everything is water at T degrees. Now, look. 1 gram of ice at -100. First, it should come to 1 gram of ice at 0 degrees. Then it should become 1 gram of water at 0 degrees. And then 1 gram of water at T degrees Celsius. Why we are going for 1 gram of water at T? As I said, in blind method, we assume everything to get converted to water at T degrees. If our assumption is wrong, we will get it. We will identify it. We will get it properly. Like the temperature will be so weird. Okay, from here I am going to get 540. So from here I am going to get delta Q as 1 into specific heat. MS delta T formula I have to use, which is going to be 100 minus T. Now here I have to first use MS delta T formula. M is 1, this is half, and this is 100. So you get 50 from here. Now here there is change of state, which is M into L. So M into L is how much? 80. And here the delta Q is going to be MS delta T, which is going to be 1 into T. Equate heat lost should be equated to heat gain. So 540 plus 100 minus T, and there 130 plus T. 540 plus 100 minus T is going to be 130 plus T. So 2T is going to be 640 minus 130, which is going to be 510. Arey, temperature is coming out to be more than 100 degrees, man. That's an indication what will be the equilibrium temperature. The equilibrium temperature is blindly 100 degrees Celsius. Why that is going to happen? Because some steam will be left. Some steam will be left. That's why. That's why. Super, Sanjay. Do this question. JEE Mains 2020. M grams of steam at 100 degrees Celsius is mixed with 200 grams of ice at its melting point in a thermally insulated container. If it produces liquid water at 40 degrees Celsius, the value of M is. You are lucky. You are lucky with this question. Why? They only said that everything is water at 40 degrees Celsius. They only mentioned that it is everything that is water at 40 degrees Celsius. So that's why I'll call yourself to be lucky. So how do we start? Obviously, we have m grams of steam. M grams of steam, which is at 100. First, it should become m grams of water at 100. At 100. And then it should become m grams of water at 40. Why? How I know that it is 40? They only mentioned in the question, man. Finally, it produces liquid water at 40. That means everything is at 40 degrees of water. Now let us talk about who is going to gain. We have ice, 200 grams. 200 grams ice at how much temperature? At 0 degrees gets converted to 200 grams water at 0 degrees. Then this is going to get converted to 200 gram water at 40 degrees. Now let us talk about this. This is change of state. Whenever there is change of state, you have to use M into L formula. So M is going to be 1. L is how much? 540. They only gave it. I didn't take it. Now, what is the delta Q? Which is ms delta T. What is M? 1. What is S? 1. 100 minus 40, which is going to be how much? 60. Now here we have delta Q. Why did I take 1? My bad. I shouldn't take 1, right? Because they have given M mass. My bad. Sorry. I have to take M. I have to take this to be M. Okay. Delta Q. Here what is happening? Change of state. So M into L. That means 200 into 80, which is going to be how much? 16,000. Now here delta Q is ms delta T. What is the M value? 200. What is the specific heat? 1. What is the change in temperature? 40, which will lead to what? 8,000. So total how much heat is gained? 24,000 heat is gained. How much heat is lost? You can say 600 M. So heat lost. 600 M is going to be equal to how much? 24,000. Is going to be 24,000. So the capital M is going to be how much? 40 grams. 2 zeros, yes, 40 grams. So the mass of steam we are talking about is 40 grams. 40 grams. Okay. Take this. A copper ball of mass 100 gram is a temperature capital T. It is dropped into a copper calorimeter. Man, I just want to talk about, where is that? I just want to give you info about calorimeter. See, calorimeter is going to be containing some vessel, right? Majority of the times they are going to have, or the container is going to have some liquid, which is going to be mostly water. right? This whole setup is going to be put into wooden frame. This whole setup is going to be put into wooden frame. Why they are going to put that into wooden frame? Because why they are going to put it into wooden frame? Because wood is a very bad conductor of heat. As a result, no heat goes from this container to the surroundings, or no heat enters from the surroundings to this container. Even this should be closed with a wooden lid. As a result, what is happening? Whatever the heat will be there inside this calorimeter will be within it. No, nothing goes out, nothing comes in. So if you want to throw some hot body, you will open this wooden lid, you will put that hot body into it. You will put that hot body into it. So when the hot body goes in, the hot body will be giving heat to the liquid as well as the calorimeter, that vessel. Who are going to gain heat? Water and the vessel. Who is going to lose heat? The hot body. Now you solve the question. We are almost done. We are almost done. We are on the verge of completing this. We are on verge of completing this. We are almost done. A copper ball of mass 100 gram is at temperature capital T. It is dropped into a copper calorimeter of 100 grams filled with 170 grams of water at room temperature. Subsequently, the temperature of the system is found to be 75. Man, who is going to lose heat? Obviously the copper ball. Heat lost is going to be equal to heat gain. Man, here how many are gaining heat? Water as well as that vessel, copper vessel. Okay, copper ball, the copper ball, right? 100 grams of copper ball. So 100 grams of the copper ball, which is at T degrees Celsius, ultimately came to what? Ultimately came to 100 grams of ball at how much temperature? Finally, they said that it is at 75 degrees. So delta Q, I should use ms delta T. What is M? It is given as 100. What is the specific heat of calorimeter? 0.1 calories. Into what is the change in temperature? Obviously T minus 75 I have to write. I have to write T minus 75. Right? So how much heat is lost? So the Q lost is going to be 10T minus 750. Why 100 into 0.1 will be 10. So this much. This much is the loss. Who is gaining? Man, gain is by calorimeter as well as water. So directly I'll write it down. Gain, the delta Q gain is because of two of them. Who are they? Copper. So I should write M1 S1 delta T plus M2 S2 delta T. So copper vessel is having 100 and its specific heat is 0.1. And what is the change in temperature? Initially they were at 30 degrees. Now they became 75. So 75 minus 30, 45. Plus, what is mass of water? 170. What is the specific heat of water? 1. So water also was at 30 degrees. Now it became 75. So this. So 450 and 450 and 170 into 45. 170 into 45 plus 450 gives you 8100. So you are going to get 10T minus 750 is 8100. So 10T is 8100 plus 750, which is 8850. So I am getting the temperature to be 885. I am getting the temperature to be 885. So the answer is 1. So the answer is 1. Answer is 1. We are almost done. We are almost done. This is one good question. Okay. Please do this question also, because this is touching the water equivalent concept. After this, I'll just explain the effect of pressure on melting and boiling points. Done. This is going to take 1 minute. That's it. This is going to be like, I will explain pressure cooker, right? I'll just give you the fact. This is the last question. In fact, this is the last thing. Come on, do it. Almost done. Sorry. I have taken so long. I was giving you a lot of clarity. Problem with me is, I explain everything in so detail, because whatever the conceptual clarity I have, I want my students also to have that level of clarity. Why you are doing it, what you are doing, all those things you should have that clarity. Okay, last question, man. Last question. A calorimeter of water equivalent. They said water equivalent. That means you can replace the vessel of the calorimeter with 20 grams of water. That's it. Contains 180 grams of water at 25 degrees. Man, if water is at 25, obviously the vessel in which water is there, that will also be at 25, because they will be in equilibrium, right? They won't exchange any heat. M grams of steam at 100 degrees is mixed in it till the temperature of the mixture is 31 degrees. The value of small m is close to. Why I picked this question? Generally people will miss something. Okay, fine. Whole mixture has come to 31 degrees. Who is going to lose heat? Heat lost. Obviously steam, right? Obviously steam. How many grams? M grams. So first, m grams of steam at 100 degrees Celsius will become m grams of water at 100. Then they should go to m grams of water at 31, because finally the whole mixture is at 31. Don't forget that. Don't forget that. Now look, who is gaining who is going to gain? Obviously heat gained is going to be by the calorimeter as well as water. But look, I can treat everything as water because they gave water equivalent. So I can simply treat it as 200 grams of water. 200 grams of water at how much degrees? At 25 degrees. Finally, this one became what? 200 grams of water at 31. Okay, now let us use formulas. So here delta Q is going to be M into change of state, right? 540. They only gave 540. Now again, it is changing its temperature. So M into 1 into 100 minus 31. 100 minus 31 will be how much? 69. Here, delta Q is going to be MS delta T. M is how much? 200. S is how much? 1. What is the change in temperature? 6. So 1200 should be equated to this one, which is going to be how much? 709 M. Right? So 709 M should be equated to how much? 1200. Should be equated to 1200. So the M value is definitely more than 1 but less than 2. How many options? Shit. What happened? Why we didn't get the answer? Did I do any mistake? Pro. I am pro. 540 plus 69 is 609. This should be 609. Still we are not getting the answer. 609. So you are going to get 1200 divided by 609. 1200 by 609. 1.97. Okay, 1.97. They are asking the closest value. So the closest value is going to be 2. The closest value is 2. Right? Closest value is 2. 1.97 is what you get. Now, man, just you keep this in mind. Whenever you are trying to increase the pressure, a body wants to be in its liquid state. It wants to be in its liquid state. So, as pressure increases, if the body wants to be in its liquid state, obviously it should have more boiling point. Boiling point increases and freezing point decreases. That's it. For example, if you want to talk about water, the boiling point of water will be more than 100 degrees and the freezing point of water will be less than 0 degrees. So always keep this in mind. As you increase the pressure, any body, it wants to be in its liquid state more. Okay, that's it, man. We are done with the whole thermal physics. Right? Thanks for listening to me patiently for all this roughly 4 hours of class. Thanks for listening patiently. I was explaining dead slow. Some people might have got bored. I'm sorry for that, but that is how I am. Those who are interested, they can follow me. Those who are not able to, like those who feel it is boring, it is very slow and all those things, you can follow some other teacher. It is not that you have to stick with me only, right? You haven't paid any fee for all these things, right? So it's not that you have enrolled in an offline coaching where whether you like or not, you have to listen to the same teacher. It's not like that. It's a free platform, YouTube. We are doing it. If you are in sync with me, if my frequency is resonating with you people, it's good, fine, then follow me. If not, you can find other teachers. There are many on the platform, right? All the best. All I want is you to benefit. I am not expecting you to blindly follow me, right? And I won't feel bad also. All I will simply say is that when I'm putting efforts, if something is going to be written or something like that, then I'll say, man, if you don't like it, get out. That's my attitude, because I have learned physics to this level with a lot of hard work. Almost for everything in 11th and 12th, I have a proper logical reasoning. Those people who are already listening to me from past few classes, they can clearly understand that I have strong understanding of concepts, very strong understanding of concepts, right? So what are the next chapters? Tomorrow we are going to have heat transfer. Heat transfer won't take long because radiation I won't cover in deep. Reason being, on radiation barely there are questions which are being asked in JEE mains, but conduction part I'll cover to like as deep as possible on mains level, up to mains level or slightly mains level also. So it will be some around 2.5 hours of class tomorrow. Okay, bye, good night. Do like